It's about to start. We'll talk about code or whatever we'll talk about today. It's about to start, so please hang tight while I check that everything is okay. Sound check, camera check, lights check. How's my hair? Oh, wait, I don't have any hair. Maybe put some pants on and I am good to go. So get ready wherever you are, 'cause this stream is about to start. Get ready wherever you are, 'cause this stream is about to start. Hello everyone and welcome to day 8, 9 and 10 of Advent of Code. Jeez Louise, I'm coming to you from a place of light and with me is David. Hello David.
Hello, good morning.
So yesterday we left off at problem 8. We did part 1. We implemented part 2 correctly, but in a way that wasn't super fast. And then I asked David, like, can you keep this running overnight to see if it will complete? Because
we didn't have the time to implement the smart version, but we had the time between yesterday and today. And you did, and it didn't terminate. So the naive version was no good, right?
Yeah, although probably it could have terminated had my computer not gone to sleep. So that's also my bad. But either way, I think we're going to have to implement the cooler, more complicated version.
Which, as I heard, you did. You implemented it.
No, I didn't do it.
Ah.
I was waiting to do it with you, but I thought about it.
Well, thanks for waiting.
I did wait.
So what did you think?
But I can jump straight into it and finish it off exactly where we were yesterday.
Okay. I was thinking that as like strategy-wise, I don't know what you think is best. We could continue with this and finish it because we have the context in our heads, or to try and catch up, we could do day 9, which according to Nick was easier, and we could take a look at day 10 because I haven't heard anything about day 10. It has been released only 5 hours or 6 hours ago. And then we could return to this, which we sort of have the strategy in our heads. It's a matter of fleshing things out. So how do you want to go about this? Do you want to finish things off and then proceed, or do you want to try and catch up first?
I really want to finish this off.
So let's proceed.
Because we're so close, and I have very clear in my mind what we need.
All right then. So carry on. You're driving.
Okay. So where we left off, we just had a wrong assumption about how the cycles was the issue yesterday. So to sort that out, we need to check whether we reach this node and this I% learn instructions in scene.
Yeah, so
we've already seen that before. Now I think we can move that to the top and then add it.
Mm-hmm.
And that should get the end nodes, I think.
I also would say that the end node indices need to change, because now we need to know not only maybe it's not the end node indices that we need to change, but here's my idea. The graph, we will start at any point in it, then we are going to traverse some nodes, and at some point, because there are only so many nodes and so many instructions, we will cycle. And that's what the scene set is all about, detecting this cycle. But it's not only that. We are interested in the end node indices because we may need to go around the cycle a couple times in one of the seeds. I'm calling them seeds now. In one of the seeds, we may need to go around the cycle a couple times before it syncs up with another one of the seeds reaching a terminal node. So we need to know not only the end node indices, but we also need to know the index of when we got into the cycle, because that tail in the beginning it acts different, it behaves different. So we need to know the index in which we got into the cycle, which is the index of the first time that we found a node that later on will be the node that makes us stop in line 1607.
So I think, so there's two things. There's the index inside the instruction set, and then there's the index which is monotonically increasing, if I'm using that correctly.
Yeah.
Which is, we never modulo, right? And that's I, and that's what the end node indices are. And isn't that what you're referring to? We just need to know the absolute value of I.
No, it's not just that. It's the fact that when we go around this, and by the way, I'm surprised that this is day 8, because this, if I understand it correctly, and there isn't a simpler solution with a simple for loop, this is surprisingly complicated for day 8. But anyway, my point here is that you may need to go around the cycle a couple times, and to compute the least common multiple and all the things we'll need to do later, we don't want to compute the least common multiple of the index in which we found that terminal node when traversing from the beginning. We need to take in account that when doing the cycles, we will not revisit this tail in the beginning.
We will not revisit when we do the cycles. We will not revisit some nodes at the beginning.
Yes.
Is that what you said?
Yes. So when we use the end node indices, we are going to use that as a way of computing the LCM with something else and all of that. So in computing the LCM, we will not want to use the raw end node index. We will want to take in account the size of the tail before we got into the cycle.
I don't actually fully follow what you mean.
Okay.
However,
So, okay.
There is. We'll come back to it in a second. I just want to say there's one more issue with this, which is I'm assuming there's only 3 end nodes and 3 start nodes, and there are actually 6. So this actually needs to be it needs to be like a for loop of some kind,
Yeah.
which I have the solution for.
Yeah.
And I'd like to implement that.
Okay.
But maybe I don't know if it helps if you have a clear way of tracking that thing that you were suggesting, because you could just write that code. But I'm not really sure. It hasn't really clicked for me what your issue is there.
Yeah. No, fair enough. It's like that idea of, I guess, a drunk person trying to find their keys, and it's during the night, and they are like near a lamppost trying to find the keys, and someone comes by and says, "Oh, what's happening? You're looking for your keys. Did you lose them around here?" And then the drunk person says, No, I lost them around there, but this is where the light is. So, okay, carry on, do the things that we know how to do, and then we'll get to where it's dark.
That's it. That is pretty much it. I was wondering where that analogy was going, but yeah. So yeah, basically we're going to have these end nodes, and then we're going to need to do. I can't think of a better word than ends nodes for find end nodes and nodes, because it's. And then it's going to be like end. I think it's going to be. Yeah.
We are using Ether tools. Hooray!
Yay!
Soon.
Do you remember this?
I do. Soon
Product.
we will. Yes, I remember this. We saw it in the shorter answers to other problems, and soon we will be using default dict over here. We'll be graduating.
Yeah. Yeah, we could have used default dict for graph, but we've resisted. And then, so now, I think I think that should be the answer. But
Let's see what you have. Well, first thing that surprises me is that we have an LCM with 2 parameters, and here we call it with 3 parameters. I suppose it's a matter of calling LCM twice.
Oh, sorry. This should be with like arbitrary parameters.
Ah.
Yeah. Not sure how that's going to work.
Well, you'd want to reduce with the args, finding the LCM of 2 numbers, then the next 2, then the next 2, then the next 2.
So it's going to be this. Now I just need to implement LCM. So this does GCD. Does this? Can this? Oh yeah, this can take integers. Okay, so I can do like the absolute. Can I do math dot product?
Isn't it iter
Yeah,
tools
like
dot
that.
product?
Yeah, but iter tools dot product is about like combining. It's like the Cartesian product, so it's like the combination of all of these sets.
Ah,
Whereas math dot product is like multiply everything together.
okay.
Um, so there's the end nodes, there's the combinations. Should we have a look at what the results are? See if this is kind of working, and then if and then we can integrate your part of the solution. Is this running infinitely? Yeah, because part 2 answer version 1 is still running.
Well, it's not infinite. Don't say that. It just
It's
takes
not
a long.
infinite. It has run and it's given us.
Yeah, it's just
It's given us
very
an
long. Our solution is not that bad. Okay.
Well, there's some printing going on every time, which is not super useful. But the end nodes, weirdly, it's just one array per. There's just one end node per.
Are you seeing some outputs on the terminal that I'm
per
not?
map. Yes. You're not seeing any. Oh, it's because I've got multiple terminals. Let me close some of the other ones that I'm not using. Okay, let's run again.
Now I see. Now I see end nodes, and I see combinations, and I see part 2 answer. Indeed, that is a long number for us to have done the brute force approach. Are we running with the real inputs, or are we running with the example inputs?
That's a good question.
We are-
No, it's with your real input.
With my real input, okay.
Yes. Now, that doesn't seem right. It seems like it's exiting after the first end node that it finds. Because it's saying.
Well,
I don't know why that would be.
It may be hard to
other
reason
than-
about the real input, but let's reason about the example input. If we start at 11A and the rules are LR, so 11B, 11Z, 11B.
Okay, should I comment out? Oh, you need to
11C.
share your screen, by the way. But
I thought
should I
that
comment out yours and see how it does?
I thought that the Visual Studio Code Share thing would take care of that for us. But anyway.
Okay, sure. I can follow your cursor. That's cool. I'm
Look,
following you.
I shared the screen with you on Skype as well. So we start here and we're following LR. So
Okay.
left, right, cycle. So in this case, we expect to see 11Z showing up after 1, 2 steps, and then 3, 4 steps, right? Something like that. For 2-2-way, it's 1, 2.
Yeah, I mean we can do it, right? So 11A
4,
is
5,
like 0.
and 6. Yeah. But don't write it there. That's our real input. We're gonna test this later.
But 11A and then 11. So that goes to 11B and then that goes 1, and then 11B goes to 11Z and then it goes to 0. And then the next one will be 11A. Oh no, so 11B.
Yeah.
And then it'll be 1. But that's actually not quite what the end node indices are. The end node indices are Yeah, the no, actually, maybe that is what end node indices are. Yeah, that is what end node indices are.
No,
So that's when it will
no,
stop. It will see one
no.
B, and
It
it
will be something like this. We're just counting up sequentially. How many steps did we take to
No.
get here?
I mean, yeah, but that's not what we're adding to end node indices. We're doing the modulo. That's what I is. So this is
Wait,
node.
what?
This is
No, are we?
Yeah.
End node indices append I.
percent len. Oh, that's wrong.
No, it was right. Keep that.
Oh no, that is right. That is right.
That is right.
That's right. What's wrong is what I'm saying. Sorry, what I meant to say is that's what we're adding to the set. Is the
Yes.
the modulo bit.
That is right. We want to add to the set the modulo, but we want to add to the the end node indices, the non-modulo.
Yeah, that makes sense. That makes sense, definitely.
And
You're right. You're right.
coming back to the example that we are working on, you go to B, and then you go to... wait a second. When you revisit B, you have found a cycle because you are going to B 11B, and you are in I modulo 1. Yeah.
Yeah.
So this is the end of the cycle. I agree with you on that. And we need to store the numbers 1 and 3 in the... No, we need to store the number 2 in the list of n indices. I'm with you on that.
Yeah.
But there is more to the story. Do you want to hear the more to the story now?
Yeah, definitely.
Okay, so there is more to the story, and that's the part that I was trying to explain before, but I think that explanation will go better now that I have an example in front of us. So I want to separate this journey, this story, in 2 acts. Act 1, we work from the start point to the start of the cycle. In this case, we know that the cycle is going to be this much. So Act 1 is really just this bit, getting us from the start to the cycle. And Act 2 is going around the cycle. We may repeat Act 2 many times, because we may need to go around the cycle many times before we find the true end condition to the problem, right? And
yeah.
in general, we are running this thing in parallel. So we are running 11A and 22A in parallel. So we may need, in the general case, not in this specific case, but in the general case, we may need to go around the cycle of 11A, or the journey of 11A. We may need to go around its cycle many times before 22A settles down and finds an end condition simultaneously. But Act 1 doesn't repeat. So we need to know when Act 2 starts, because when we are going around the cycle, which in our case is this computation of LCM, when we are going around the cycle, we must not go around the cycle including this part of the story. We must only include this part of the story. So when we say that we are storing I, that is important and it's a big deal, but we need to store I with respect to this cycle as well. So when we are doing the LCM, we need to know that the cycle really started in index 1. So we are doing the LCM of everything minus 1. We need to do 1 minus 1, 2 minus 1, and 3 minus 1. And we need to add the length of the Act 1 to the results.
Yeah. God, yeah, you're right. Yes. Okay, so we have something like going back to the end node indices, we now need to massage the result so that it works, right?
It's I'm not sure how to feel about this. The way that I'm reasoning about this is perhaps we should return two things from this. Let's say that this is the phase of the algorithm in which we are learning about the cycles. And I would say that the learning of this is not only the end node indices, there is a second thing that we learned along the way, which is how long did it take us to get to Act 2?
Yeah. So that's the cycle found index thing, I guess.
Perhaps.
Is it this that we want?
It's not
might be that.
quite. No. You don't. When thinking of the lengths here, the length of Act 1 and the length of the cycle, you never want a modulo. Because while we are in the middle of the cycle, we are going around the instructions over and over. So you never want a modulo in that case. That's that case. It's the same argument for not moduloing in the end node indices.
Yeah. Okay, so that makes sense. So now we have the cycle found. We're going to need to... I guess all we really need is I, actually.
So the way that I imagine this is like so. Coming back to the example at the top, is we don't know when, with the information that we have collected in our auxiliary function so far, we don't know what was the I back when I found the start of the cycle, 1,1b. And we don't know that because we don't know that we are entering Act 2. We will only know that in hindsight. When we find the same state twice, when we find the same state again, the state being these two variables, of course. So when we find these two variables the second time around, is when we realize, oh, okay, so back then in, let's say, step I equals 1, that is when my cycle started. You only know that in hindsight. You don't know that going in. You only know that when you have seen it again. So I think that what we need to do is, as we traverse, as we walk around the graph, we keep the state, which is what I selected, and the step. And then when we find a cycle, we say, okay, I found a cycle, so I'm going to stop. But not only that, I will record the I that I had back then, not the I that I have now, the I that I had back then, because now I know that that is when I got into the cycle. And that's the second piece of information we need. The first piece of information is what we already collected.
Got it.
The end indices for the end nodes. The second piece of information we need is this number 1 here. And just that will be enough for us to put everything together and find the solutions later. While they're doing that, I'm gonna peek at the chat because maybe Nick is gonna be like, you could do that with a simple loop. No. I'm not getting anything. And
I guess the question is, how do we now use that information? So what we know is that...
Let's first double check that we collected the right information.
Sure. We can have a look. So we found a cycle index 6 is what I've got at the moment.
Do I have another terminal again? Because I don't see cycle index in the output from the terminal.
Yeah, You should be able to
Yeah.
have another check.
Maybe it's one of those things with live share goofing up. Well, never mind that. You're telling me the outputs, and that's good enough.
Well, that's the current output.
Okay.
So these are the scene.
And the cycle
And
index is
then-
not supposed to be 6.
Saying it's cycler. No. Is this the right input we're looking at? We didn't uncomment it? Yeah, we didn't uncomment it.
Good point.
Yeah. Let me just pop that in.
Am I in the wrong terminal? No.
Oh, I'm going to close this terminal and then create a new one. And then maybe this will work for you, but yeah. You can also try quitting my... Oh yeah, make terminal read write.
Okay, I have the terminal. Thanks.
And now try running.
Yeah, I see the outputs now. So,
Okay, cool.
we have seen let me see, 1 at index 0, 1 at index 1, and 1 at 2. And then we stop. That is
Yeah,
because
so
we are
this
gonna
part of it
find
is
one
not
one
so
B.
relevant.
We are gonna find 1 B on the next step, and then that's when we stop. Okay. And sorry, I didn't hear what you said.
No, just that like these are two separate because we've got two different root nodes. These are like the scene is and the cycle index are two different things, right? But it's cool that we're actually seeing two different. We're seeing 3.6 there, so that means it's kind of working because there's two different end nodes before we hit a cycle for the second example, 2A, 22A.
We see 22Z, and then we see 22Z again.
And it actually gives us the right answer.
It does. And it only gives us the right answer, though, because for this particular example, you don't have to go around the cycle multiple times before it settles down. Am I right?
Yeah. Yeah.
Or does it?
I
I
think-
think 1A goes around the cycle multiple times.
Yeah, but maybe it doesn't matter because it's multiples.
Yeah, I think that by coincidence this one works, but I think in general my problem with Act 1 and Act 2 still applies.
Yeah. Yeah. Because the offset thing, right? Because even if you can't just multiply, if you got to like index 3, if the cycle was at index 2, you can't just multiply index 3, 10 times or whatever to get to the next one, because you'll only cycle whatever the cycle is. You need the cycle length to be able to get what the multiples are of it.
Yep. And this part of incorporating Act 1 into the story really makes my brain hurt.
So if you had, let's just do some examples here. If you had like 1, 3, 6, these are like the, let's say just 3 and 6 were the end node indices that we found for a particular graph. And then we had another one and the cycle index was at step 2, let's say. And then we had a different one which was end node indices at step 4 and the cycle index at 3. How do we find where these converge?
That is the part that makes my brain hurt, because there are, at least in my head, there are some different cases in which the first end node index is actually in the tail in this Act 1 situation, right? We could not even need to get into the cycle. We could just find our end node in the way there. And we need to take that in account as well. And then after we get into the cycle, that's relatively straightforward, because we just take the cycle index and subtract every end node index, and we should be good to go, right? If we got to the cycle if we got to end nodes in indices 3 and 6, and our cycle index is 2, it means that when we go around the loop, we will find them again in indices 1 and 4. 1 being 3 minus 2, and 6 minus 2 is 4.
So if the cycle index is... So just to expand on this example, if it's 3 and 6 and it's 2, that means that when we get to 7, 8, and then 9, I guess, well, actually, I probably would be the 8. I'm not sure about, maybe off by 1s here. But 8 will be a stop indices, right? And then it will be 9. Do you see where I'm going?
Yeah.
Like I'm trying to count it out.
Yeah.
Well, actually, would it be? No, it's not 8. I'm doing that wrong. Like we need to create because we equally couldn't say it's like, we couldn't just say like 1 and 4, because 1 and 4 aren't end node indices. Yeah, this is making my brain hurt too.
Yeah, I think unfortunately I will need to draw some diagrams here.
One interesting thing we could look at is because there were only like one end node index before we found a cycle. If it's less than the instruction set, then we don't need to worry about this too much.
Less than the
You see what I
instruction
mean?
set? What do you mean? What is instruction set in this sentence?
Yeah, so the length of instructions, so it's like left, right, left, right, left, right. If you count all of those, if we never need the modulo, because the cycle is found before we hit the end of the instructions, then we don't need to worry about this offsetting.
I don't see how the length of the instructions
Is that right?
affect this issue here.
Okay.
Shall I draw a diagram?
Go ahead. Yeah, go ahead with the diagram.
Okay, I am gonna draw a diagram of the example input all the way up top here. 1, 1a goes to 1, 1b goes to 1, 1z goes to And not only that, but in terms of how many steps we took, we took, in this case, 1 or 0 at this point. Then here 1, here 2, and then when we are back, would we need to store this? Would we need to store the cycle size? Yeah, I suppose. So from this story that I drew, what I will want to know is the indices of all the end nodes. We call that the end nodes indices. I will also want to store how long it took me to find the cycle. So I'll call this the cycle start index, or I guess you call it the cycle index. I'll call it the cycle index. I will also want to know the cycle length. And I think that with these 3 pieces of information, we should be able to determine the answer. Now, how do we use these pieces of information? Let's find them for this example here. So end node indices is 2 in this case. The cycle index is 1. That's when we got there the first time. And the cycle length is 2. We visit 1, 2 nodes before we get back into the cycle. All right, and it should be the case that the cycle index, I will take note of this here on the side, it should be the case that the cycle index plus the cycle length should always be equal to the length of the journey. The length of the journey being how many states will I have found when I stop, when I break out of the search. Now, let's do the same exercise for the other cycle we will find in this example.
Leandro, sorry, I've just got to run for 10 seconds and I'll be back. Is that okay?
Do you want to turn off your camera and your microphone?
I can certainly turn off my microphone.
Yeah, okay.
Yeah, I'll be back in literally. Actually, no. Let's just keep going because you're so close here. So you're saying
no, take your time. Take your time. I will be here.
I agree with everything you've said.
Yeah,
so far.
I will be drawing diagrams while you're away.
All right, 10 seconds.
Take your time.
Bye.
Here I am drawing some diagrams. I really hope that there is not a simpler solution to this problem, because geez Louise, this is a complicated problem. 2 to B, and we are going to the right. And 2 to C, and we are going to the left. And we are now in 2 to Z, and we are going to the right. Not that it matters because both are the same. Oh, and I should be keeping track of which instruction I'm using. I will keep track of which instruction I used to get here. So in this case, I used instruction 0 to get here.
I'm back.
Hello.
Sorry about that.
Don't worry.
Sorry.
I'm also keeping track of something else. I'm adding more information to the graph or to the drawing. So maybe I should draw it differently. I want to know which instruction I used to get here. Did I use a left or a right to arrive here? That's part of the state. So I guess I will draw it like this. So this will be a poop, because to begin with, we did not use any instruction to get here. Or should it be a poop? Should it be -1? Should it be 0? It's complicated for me to tell right away. But there is something for us to do in this situation. Then I got here using L, which is instruction 0. I will number these instructions as well. And I can remove this bit. And here, I got here using instruction 1. And then I got there using instruction 0. So all of that checks out. In parentheses, we will find the i's and the slash, and this is like the instruction, or maybe even I modulo length. Like so. And this is the node label, for instance. Okay, so that is the notation that I'm making up. And in light of this new notation, do you have an idea of what we should put here in the poop? Because I feel like there is a principled thing for me to put here. I think perhaps it should be the length of the instructions, because it could be the case that this guy is the beginning of the cycle.
I don't know. Feels like maybe it's still too early to give that something. Where are you trying to go with this? What's the...
It's complicated. This problem is...
If it's the length of the instructions, then it should be 2.
No, the length -1. It should be the last instruction, because if it is the case that this guy is a cycle, if it was the case that this arrow actually pointed back to the beginning, then we would have arrived here by using the last instruction, because we are about to use the first one again to get to the second one. So yeah, we must start this state like so. In this case, it is the index. I shouldn't say the length of the cycle. It is the index of the last instruction, which is in this case R1.
That makes sense. Yeah.
Jeez Louise. Okay, so
yeah,
let's try and do this for the second cycle we will find, which starts in 22A, and then it's 22A/1. That's our I0. Then 22B/0, because that's the instruction I used to arrive here. Hang on. Maybe instead of thinking of this slash something thing as, or this slash something thing as the step I took to arrive here, I should think of it as the step I'm about to take. And then everything falls out more easily, because then this starts at 0. So I'm about to take step 0, I'm about to take step 1, and I'm about to take step 0. And these are just identifiers for the states, so it doesn't really matter which way I do it, as long as I'm consistent about it, but I think it's more convenient to use this. So I am in 11A, I'm about to take step 0. I am in 11B, I'm about to take step 1. I'm up in 11C.
Yeah, I think this is what we're doing.
Yeah, that's better. So I'm in 22A, I'm about to take step 0. I'm in 11B, I'm about to take step 1. I'm in 22C, I'm about to take step 0. Okay. And this is where I stopped. So now I am in 22B and I'm about to take step 0. So that is going to take me to 22C. And I am about to take step 1. Or instruction 1. Which will take me to 22Z. And I'm about to take step 0. And then I am in 22Z, and I'm going to 22B to take step 1. So I'm cycling back to this fellow. How does one type that sign that you have there? Like so, okay. That I have there, in fact. Let's review our work. We start at 220, or 22A, and we are about to take instruction 0, which is the left. So we are going to 22B, and we are about to take instruction 1. So we go to 22C, and we are about to take instruction 0. And then we are in 22C, and we are about to take instruction 1. Then we are in 22Z, and we are about to take instruction 0. And then we are in 22C, and we are about to take instruction 1. Then we are into 2Z, and we are about to take instruction 0, which takes us to 22B, about to take instruction 1. Okay, I have reviewed the work, and it seems okay to me. So now let's compute these things. The end node indices, they are everything that ends with a Z. So it should be these two people, 3 and 6. When did I get into the cycle? I got into the cycle in step 1. And what is the cycle length? It's how many elements I have in the cycle, right? So it's 1, 2, 3, 4, 5, 6. And indeed, if I start here, I take 1, 2, 3, 4, 5, 6 steps, and I'm back to where I started. Jeez. Okay. So because of the values we have on the screen, it is the case that in our situation, by coincidence, the answer is 6, which happens to be the minimum common multiple of 2, 3, and 6. So the problem works out in this particular case, but it won't work in general. So now we have an example in front of us. Can we look at this and have any intuition as to how we use these numbers to compute the answer? It will have to do with the cycle length. It will have to do with the cycle index, which needs to be subtracted from here when we are doing the cycles. And it will have to do with testing every possible permutation of these numbers against those numbers, or maybe not even permutations, every possible combination.
An interesting fact is that this is only length 1 for the real inputs. In this particular scenario, it has a length 2, but for the real inputs, it's only ever length 1. There's only ever one end node, unless the code is wrong, right? But
what?
It doesn't matter though, because I've written the code for the combinations anyway.
In the real inputs, in the
product.
real inputs, we're never gonna see end nodes twice. Is what you're saying?
Yeah, before we reach a cycle, we always reach a cycle before we see another end node index.
How do you know that?
Because we computed it. These are the end nodes for
you mean
the real
what we
input.
see in the terminal?
Yeah.
And you're saying that in all of these inputs that doesn't even fit on the terminal, you have found some property of the end nodes? I'm surprised. I don't think I understand
I
what
mean,
you're
if
saying.
you, I don't know why you've got a second, like different terminals to me. This is the output from my terminal.
Should I be following your
I'll just-
cursor?
Don't know if that helps. There seems to be some issue with the terminals, doesn't there? But this is the output for, at least for my input. You can run your input as well to see if that's true. But the end nodes, this is for the first starting point, second starting point, third, fourth, fifth, sixth, before we find a cycle. And you can see we reach 1394. There's only 263 instructions. It takes us 1400 steps to 2100 steps to actually reach a cycle, but we only find one end node index in each of those.
Could it be that the example input is more
But the end
complicated
node-
than the
The
real
end node
inputs?
could be, but the end node the cycle indexes are 3, 2, 2, 5, 2, 2, 5. So they're pretty. You come back pretty early on in the length of instructions. So the cycle index being where in the instruction set, the offset within the instruction set.
Wow. If that's the case, we could use that as a simplifying assumption, but it would be surprising to me if that held in general, because in the example that was given that was much smaller,
It'd be hard to design that.
the property didn't hold. And besides, how come we have so few end nodes and so few combinations? It doesn't look right to me. The real input is large, and we only have so many end nodes and so many combinations. Is that true?
Well, yeah, there's only one combination, right? But there would be maybe more combinations because of the cycle indexes, but also, I mean, an interesting property is that when I run it on our example input, it does actually come up with the right. It does detect multiple end node indices, which gives me some confidence. So this is the example output. This does give me some confidence because here you can see it's actually finding those multiple end node indices.
And that I'm confident about. Yeah, that I'm okay with.
But that gives me confidence that if there were multiple end node indices, it would find them as well. Yeah.
But what is surprising to me is that there are so few arrays in this array. How many start nodes do we have in the real inputs? Do we have only half a dozen?
Yeah, we only have 6, yeah.
Ah. Interesting. We only have half a dozen of them. But the cycles are really, really, really long, right? Because otherwise, why would our machines be unable to compute this with the naive solution?
I think it's just like maybe these are like, you know, intentionally like the lowest common multiple is an extremely big number. I mean, for these numbers, you can see how big it is. Because you've got 6 numbers, I guess it is quite hard to find one, which is
So they made only 6 inputs or 6 start points, and they made the cycle sizes large, and they made the cycle sizes almost primes with respect to each other, or maybe even primes, so that the least common multiple would be a really, really, really large number, that there would be very few, if any, common dividers between them.
Yeah.
I see that.
I'm just going to run it for your input. just out of curiosity. Yeah. So for yours also, I'll just paste. I guess this is kind of cheating, looking at different outputs, but yours has a similar characteristic where there aren't multiple end-node indices before we hit a cycle, and again, cycles are relatively early on, and the number is absolutely massive.
Wow, that's very interesting. That could be a simplifying assumption. The idea that I had in my head was kind of solving the general case that is a bit more complicated. Have you tried just pasting this answer?
Yeah, I don't want to distract you too much because I feel like you were. I did try pasting my answer and it was wrong. It was too high.
Okay.
But I guess that would make sense though with our because of the cycle stuff, right? Because it's not just multiples of this. There's also the offset issue.
And
we need to like.
If you don't take in account the offset, you will end up with larger numbers because, like I said, the way that I'm intending to use these offsets is to take like the 3 and the 6 and subtract the act 1 length. So the numbers will become smaller and therefore your answer would overshoot.
Could we find the lowest common multiple and then do the subtraction? Or at least no, I don't know if that would work, but or like subtract it and then we'll have to add the offset on again, right? We'll have to add like 3 or something to it.
Well,
won't we have to subtract and then add?
I don't know. I have some people here on the chat. Tail says, hi, just checking to see how you guys are doing. It seems to be going fine. Oh, no clues? Oh, Tail, come on, help us out here. This is so painful. This is atrocious. And, okay, I think that the thing we need to do is we need to split this in several cases. We need to split this in the case of every end node will be found before we even reach Act 2. So we will just look at the end node indices as they are. Second case, one of the cycles reaches the end node before reaching Act 2, but the second cycle needs to reach Act 2, and it may even need to go around Act 2 many, many times. That's one case. The other case is both of them will reach Act 2 and go around many times. And the reason why I'm dividing this in cases is that when we get to the cycle, we can use the minimum, the least common multiple. But in the tail, in the Act 1 part, we must not. So we need to explore a bunch of cases, like a whole lot of cases, like a massive number of cases, because we need to do the combinatorial explosion of I have reached Act 2, I have not, I have reached Act 2, I have, every possible combination for every possible input, which I guess in this case, because there are only 6 inputs, it's not so bad. But it is 2 to the power of 6 in this case. Do you see what I mean?
No, I haven't fully grasped that. No.
Okay.
I'm just like focusing on this small input and working out if we can come up with a formula for taking into account this cycle length. But I guess you're trying to do the same thing. But sounds like you're further ahead than I am.
Mm-hmm.
How does it work? Do you have a way? Could you explain how to calculate now that we have this here and this here? How do we get to the? How did we get to 6? As the answer.
That is the crux of the question. That's the part that I don't know how to figure out. I know that this information is enough. I don't know how to use the information. That is the problem I'm having. But let's try and work this out. Well,
Yeah.
and in this example case, it doesn't help that the cycle index is the same between the two. Oh, shucks. Because that lines things up.
But that's fine. We can. Yeah, but if we can make it work, then we can always change the numbers afterwards. And if these numbers play nicely, so be it. But we can tweak that once we have a general idea of how to do this, maybe.
Okay, so let's suppose that there are no actual ones.
It is happening actually. If we Mm-hmm.
Are you working on something? Because I was waiting for you to say something.
No, go ahead. Go ahead.
Okay, I see your cursor moving and you typing things, and I thought you were in the middle of presenting an idea. You are, aren't you?
Oh, good. It was a half-formed idea. It's a half-formed idea. I'm just trying to think about it intuitively. I'm just thinking like this is how to see it, right? There's a cycle going on here, potential cycle going on here.
Mm-hmm.
And we just need to know the absolute number which is taken here. I guess we need to know like if they started, if we was just to draw it schematically. So here there's a cycle, and then we have something else which is here, and then here there's a cycle.
Mm-hmm.
And then at some point these two are going to align, right?
Yeah.
And these are going to be of equal. After this is like a little bit longer, just so that it's clear that these can be anything.
Well, you kind of made a special case there because let's offset the starts.
So like that. How's that? So like at some point, these are gonna overlap, right?
Mm-hmm.
And what we need to know is these are going to overlap when the lowest common multiple of this length and this length come together, but this one needs to be offset by a certain amount. How do we integrate the length and the offset?
Yes,
is the difficulty.
Yes. So, if they had all started synchronized, then that problem is simply the least common multiple between this length and that length. So we know how to solve that. But because they are not synchronized, then I want to work out a small case using your syntax. So let's say that we start synchronized and we are working with the numbers 2 and 3 because we know that the least common multiple of 2 and 3 is 6. So this is length 2 and it cycles again. This is length
Yeah.
3, and it cycles again. And here we are at the number which they match. So that is number 1, 2, 3, 4, 5, 6. Is that right?
Yeah,
1,
nice.
2, 3, 4, 5.
Yeah, so for that we
6.
can do the lowest common multiple. But what if we add an offset to one of them?
What happens then? Then they are actually gonna match here at 1, 2, 3. Because 1 plus 2 times 1 is equal to 3 times 1, or in general, I guess, 0 plus 3 times 1. This 1 is the offset, this 0 is the offset, and this is how many times are we going around the cycle. And this is correct. 1 plus 2 is 3, and 0 plus 3 is 3. So that is correct. Okay.
That makes a lot of sense. So the general formula is offset plus actually, because we only have I think all we need to do is like end node index, because we know there's only one end node index in the cycle.
Mm-hmm.
Yeah, and so on.
Well, the problem in doing it this way is that you are using
Now,
the
that
offset in the
assumes-
multiplication.
Yeah, this doesn't quite work, does it? Because this is not. We could find. Could we find a counterexample which won't work for this? Because the end node index, yeah, like you say, this is finding the LCM of the offset plus the end node index, but that's not quite what we want. Because if this was like an offset of. Yeah, so what we need. Okay, what about if we don't use LCM and we just try and calculate this?
Do you want to go to day 9? Come back to this later? This is incredibly complicated. I
Okay.
have no idea how people are solving this one, because it takes a day. And maybe there is
Yeah.
like a theorem out there somewhere that we don't know about that is exactly this, and it solves the problem, and we just don't know about it. Like Nick said, if you have the right domain knowledge, this is not so complicated. But it seems like there is an algorithm like there, like we said, Dijkstra's for finding the shortest path, and it's like a standard problem in computer science that we have never heard about, because this is like way out there. It's very difficult, right?
Okay. I feel like we could do this.
I know you
With
can.
enough
It's
time.
just that I wanted to make
And
progress,
I
because
also feel
otherwise
like we're
tomorrow we'll be doing 4 days.
Yeah, I agree. So let's get some under our belt, and then we'll come back to this, and we will solve it. And I will do some thinking about this as well.
Yes, I have some intuition.
Because I feel like this representation feels so.
Feels so what? Does it feel right, or
So
does it
good.
It feels good to you. Yeah, it feels good to me as well. I feel
Yeah,
like
it feels so.
should be
It feels so
possible.
right.
I feel like it should be possible. So I am moving some things about here because I want to leave some extra clues that I thought about. The clue that I'm thinking about is that we should be able to find this initial state over here somewhere. The initial state being, I put an arrow where we do find a match, and I'm putting another arrow where over here I'm putting like a, I don't know, a poop. And over here I will try and find this poop over here. So it's a state where this fellow is starting and the one above is a dash. So it would be here. This is the first occurrence of poop over there. And then you removed my poop. Why do you keep removing my stuff?
Sorry, I pressed undo, but we have a shared undo stack. That's really stupid. Sorry.
Do you see what I mean? If we can find the poop in the original example, then we could work on from there.
What is the poop?
The poop is the original state of the offset poop stuff. And this is the corresponding original state. You see how the original state here is the line below has a pipe and the line above has a dash. And in this, the poop is the first occurrence of the pipe dash combination. And indeed, if you count from the poop to the carriage, you will find that the answer is correct. It is 1, 2, 3.
I had another idea, which is if we have offset 1 equals 1 and end node index equals whatever it was. Was it? It's like end node offset within cycle is say let's say 2, and we have offset 2 equals 2, and then look, offset is 3. Could we just not write a for loop instead of, you know, traversing the graph indefinitely and just do those multiples? So if we had like, if it was just this, it would be like for I in range, well, it would just be like while true, and then we have I equals 0 and j equals 0, and we do something like something like if not this, I multiplied by the end node offset within cycle equals j, something like this, right? If we've reached that, then this is our return the answer. Otherwise, sort of, I mean, this is really bad pseudocode, but like increment I and increment j somehow.
The
Basically
trick is that you don't want to increment I and increment j. You want to increment
I know.
then on the next step you want to decrement I, increment j, and then on the next step you want to increment I again. You know, you want to do a count up, let's say, because you want to try every combination.
You have like multiple pointers kind of thing. Yeah, but like this kind of structure, rather than using a clever lowest common multiple, like once we have these offsets and offsets and end offsets within the cycle, we could write an algorithm which does this
We could.
potentially.
I suppose yes.
And that might complete before we die.
I agree. Yes. Because there's less work than working through every step along the way.
Yeah. Yeah. Bit troubled by that algorithm, but I feel like I could write that. Should we do day 9?
I think-
do day 10,
Yes, let's.
or should we try and write
Let's.
that?
I wanna
Yeah,
okay.
okay.
do day 10. Bo is
Oh,
asking.
you wanna
we
do day
are
10?
working on day 8. Day 8 is killing us. Day 8 it's taking forever. But we are skipping to day 9 now. And
Yeah.
do I drive this day 9?
Yes.
Okay.
Yes, you do. You do.
Okay. So I will.
You're gonna share, yeah?
No, I was thinking of just using our machine,
Okay, sure.
and we are calling it like main.js, I suppose. And here we are.
Yeah, I don't have support for MJS. I don't think.
Well, do you have Node installed?
I do. I do have version 20 of Node.
Well, there you go. That's it.
Okay.
MJS is just a way of saying I want you to use ECMAScript modules. And with that,
Yeah.
let's go to the list of problems. Day 9. Forget about day 8.
What?
I don't like day 8.
Wait, didn't you say day 10? Okay, day 9. Okay, cool.
Mirage maintenance. You ride the camel through the sandstorm and stop where the ghost's maps told you to stop. The sandstorm subsequently subsides, somehow seeing you standing at an oasis. The camel goes to get some water and you stretch your neck. As you look up, you discover what must be yet another giant floating island, this one made of metal. That must be where the parts to fix the sand machines come from. There is even an hang glider. Okay, that thing. I would totally try this. I think it's amazing.
Have you tried
No,
it?
I have not, but I would totally do that.
Em Lagoa da Conceição, que saudade que eu tenho da minha lagoa. I used to work in Coworgic, and from the office you would see people hang gliding from the mountain. It was really nice.
What I did there was paragliding. I exactly there in Lagoa.
Maybe it was. Yeah, I think you saw both when you were there. But yeah, there's a lot of paragliding.
Yeah,
going
I
on
did
there.
paragliding. It was amazing. I would totally do hang gliding, but that one is like faster. Paragliding is more contemplative. And speaking of contemplation, I need to contemplate where I put my charger because my battery is running out. And I also need to find an outlet here. So, okay, I found an outlet, but it's kind of far. I think I'm gonna have a power issue here. Well, anyway, I will stop and try and find our charger. And meanwhile, you entertain us with some more of this madness. I'll be right back.
All right. Okay, so I'm going to try and write this algorithm, which I suppose I do want to try an algorithm which does something like I equals 0, then j equals 0, then I equals 1, j equals 1. No, j equals 0. Do I want to do I equals 2? So like coming back to this one, it could be multiple cycles of I, and then, or multiple cycles of j before I reach I don't know how many cycles of j it's going to be. What I do know is one cycle is going to be smaller than the other. Don't know if that's going to be helpful. I feel like I should be able to work out add the offsets afterwards.
I managed to plug in, so if you want to get out of your misery, we can come back to problem 9.
Let's come back.
Well,
I solved it while you were away, by the way.
oh, that's excellent. I will watch the live stream later for the great insight.
No, I didn't.
Once the sun rises and heats up the sand, you might be able to use the glider and the hot air to get all the way up to the metal island. While you wait for the sun to rise, you admire the oasis hidden here in the middle of Desert Island. It must have a delicate ecosystem. You might as well take some ecological readings while you wait. Maybe you can report any environmental instabilities you find to someone so the oasis can be around for the next sandstorm-worn traveler. You pull out your handy oasis and sand instability sensor and analyze your surroundings. The oasis, cute. It's the initials, OASIS.
Oh.
Produces a report of many values and how they are changing over time, your puzzle input. Each line in the report contains the history of a single value. For example, to best protect the oasis, your environmental report should include a prediction of the next value in each history. To do this, start by making a new sequence from the difference at each step of your history. If that sequence is not all zeros, repeat this process using the sequence you just generated as the input sequence. Once all of the values in your latest sequence are zeros, you can extrapolate what the next value of the original history should be. In the above dataset, the first history is this line. Because the values increase by 3 each step, the first sequence of differences that you generate will be 3333333. Note that the sequence has one fewer value than the input sequence because at each step it considers 2 numbers from the input. Since these values aren't all 0, repeat the process. The values differ by 0 at each step, so the next sequence is 0, 0, 0, 0, 0. This means you have enough information to extrapolate the history. Visually, these sequences can be arranged like this. To extrapolate, start by adding a new 0 to the end of your list of zeros, because the zeros represent differences between the two values above them. This also means...
Leandro,
yes?
can you recap a little bit? My brain's a bit fried from
Fair enough.
day 8.
Fair enough. So start with... We are going to do this for each of the lines on the input. There are different measurements of different quantities. So you start with this one. This is the first measurement, the first line above. And then you do the difference. So 3 minus 0, 6 minus 3, 9 minus 6, and so on. And you get the second line.
Okay.
Then you do the same again. 3 minus 3, 3 minus 3. And you do that until you get a row of zeros.
Okay.
Then, to do the prediction, the extrapolation, what you do is you add a 0 here to the bottom and then compute your way up. So what would be the value that would make this a 0? What is the A that would make this a 0? Not a rhetorical question.
3.
3. So 3 minus 3 is 0. Perfect.
And 18.
And then what is the value B that would make A 3? Yeah, so yeah.
18.
So in essence, to go up, you say 0 plus 3, 3 plus 15. And that's what we get. Okay. Finding all differences for the second history requires an additional sequence, but to go up, we do the same thing. So we are just computing the nth order derivative.
Is it a derivative? It's very fancy.
Yeah, well, derivative is just a difference. So.
Right. Yeah.
And I'm sure that there is some mathematical underpinning to the way that these predictions are done.
Yeah.
But we are going to ignore all that and do the brute force solution first. And if you find the next value for each history in this example and add them up, so it is going to be 68 plus 28 plus 20 plus 21, no, plus 18.
Yeah.
You get 114. Analyze your Oasis report and extrapolate the next value for each history. What is the sum of these extrapolated values? Get your puzzle input.
Makes sense.
And I can see that there are some negatives. I can see that the lengths seem to be different. Some of them seem to have more numbers than others. Maybe it's just because they're bigger numbers.
Negative's interesting.
But I'm all right with that. I will get going here in JavaScript.
Oh, I feel like you're going to smash this one.
I will take my input. Thanks for the confidence. I need that after problem 8. I will do a sum that will start at 0. I will do for line of input split in the new line, but filter by line such that the line when trimmed is different from empty, so I ignore empty lines. Then for then I will do a bunch of things. What is the best data structure to use here? I think I'll just use an array. So for my numbers that are going to be the line split at the space, I will trim the line just in case. And I will map a number string and turn them into actual JavaScript numbers like so. And are there any peekaboos? Any numbers that have a syntax that JavaScript would not recognize? I don't see anything. So that should be good. And I will console log my numbers to check that my parsing worked. Can you... My terminal is frozen again. Can you please run the program?
Try creating a new terminal.
I create a new terminal on my machine.
Okay, I've created a new one now. So you just want me to cd into 9. 1 sec. Hey!
Okay, the parsing is good. So now I am going to start doing the derivatives. But I will need later the last numbers, so I'll need to go up. So I know that I will need something like a const last number in derivatives, and I will accumulate like so. And my current derivative will be, maybe I can just do it here. Yes. So I have my numbers, and while it is not the case that every number is equal to 0, I will compute some new numbers that later will become numbers, and my new numbers are gonna be each of, let's say, number index starting at 1, number index less than number's length, and number index going up. New numbers push numbers at number. I hear a Skype thing. Is that you, David?
No. What Skype thing?
I hear a brrrr on Skype. Whatever.
Not me.
-1, and then I will push into my last numbering derivatives the new numbers at -1, not flat, at. Okay. So let's see what we have just written to see if we agree. I think that this parsing is okay. We have already checked that. Then we are accumulating the last number in derivatives. Then while it's not the case that every number in the numbers is 0, I'm going to start computing the new numbers. I could do this in place if I wanted to be cute. I don't need to create a new numbers array.
So while you haven't created the bottom row, is that right?
Wait a second. I'm considering whether I should do this in a cute way and not accumulating into a new numbers array, because it could be potentially faster for part 2.
Wouldn't second guess part 2.
Yeah, no. Yeah, and sorry, can you say that again? Can you ask again?
Yeah, I'm just trying to understand this algorithm. So this is like while we haven't reached the last row?
Yeah.
Is that right? Okay.
So while we have a list of numbers that is not all zeros, or I could write this in another way that would perhaps make it easier, because here there is a double negative kind of going, or no, not a double negative. Yeah, I will leave it this way. I was gonna perhaps change this into
you could do it's sum, I think.
Yeah, but with the sum, I would have to go to the end even after I find a non-zero.
Yeah.
And this stops earlier. It short circuits.
Mm-hmm.
So new numbers, and then number index starts at 1 because we want to do a -1 later. And then we push.
And then you set numbers to new numbers, yeah.
And these last number derivatives should indeed have an element to begin with, which should be, maybe I shouldn't call this the last, just call this the last numbers, because even on the first line, which is not a derivative, it should also be there. And this should be numbers at -1. And I think I agree with what I just wrote. And then to work our way back up, this is always going to be a 0. So the work to go back up is just to sum all of this. If I sum 1 and 6 and 28, I get 21, I get 28. So what I want is just the sum of all these last numbers, which means that I don't need to compute the last numbers. I just need to sum them up. So I will say that this is my prediction. like so. And then in the end, I will add
Very efficient.
my prediction. But it's not only that.
Yeah.
I could wait. But it doesn't really make a difference. Right?
Because I probably would have followed their whole examples and computed the entire grid of everything, and I think this is really...
This makes debugging a lot harder, but it will be the most efficient thing that we can do without optimize new numbers in line. We don't have to create a new array and then replace. We could just replace numbers because we will never need these numbers again to the left. We are just caring about the ones on the right. So we could say that 3 minus 1 is 2, and we could replace this number 1 with the number 2. Then 6 minus 3 is 3, and we could replace this number 3 with the number 3. But I won't do that. I will just run it like this and see if you will run it for us, because I cannot even save anymore. Can you?
Running into an issue. Plus plus. Yeah, you need to do
114.
114 is the answer for this input, which is correct.
Yeah, it is the correct answer. So now let's grab this big.
There.
Ah, okay. Me here.
Okay. So,
Me here.
okay. Sorry. Sorry. Okay, I've stopped editing.
Even follow your cursor. You can continue.
No, the only thing I was doing was making sure that it's easy to uncommon and common examples. That's all, by adding region. But now I'm done. So over to you.
Okay. What could be going on here? Number representation is a good, reasonable guess. So I will stop following your cursor and I will turn this into a big int. And then I will... And now I was able to... I cannot use our terminal. Enough of this. I'm copying and I'm going to my machine and I'm doing a live share with you.
Okay. By the way, it could be Abby's InstantNet.
Yeah, absolutely. Because I am doing a call as well.
Maybe just, you can, and it's slow to update anyway.
Okay. There. And that. Wait a second. I'm closing all of it. Okay. Almost. Okay. Now things are running on my machine and live share shouldn't be so annoying. But you do have the link and you can join, right?
Yes, I can.
Okay.
Okay.
Wait a second. Your first half of this puzzle is complete. It provides a gold star. Okay, so it worked. Advent of Code was goofing out. Enough of that.
Oh, okay. Were you trying to submit it to part 2?
Perhaps. We can revisit this stream and figure out what the hell happened. And it was probably me goofing around and clicking the wrong buttons. But what matters is that we have the right answer for part 1. Let's skip it.
Great.
And I will just tidy it up and confirm that it is working. And confirm that as well. See anything different?
Left-hand side. Toggle.
Yeah.
A little, like, carrot.
Perhaps it's some
As if
setting
it's
that I
not
don't have
muffled.
or an extension that
Do
I
you
don't
see that?
have. Because I don't see any carriage. That's all right.
I also no longer see it, but I did see it before.
Maybe it's live share that is
Okay, never mind.
making that happen. Of course, it would be nice to have even more. Surely it's safe to just extrapolate backwards as well, right? For each history, repeat the process of finding differences until the sequence of differences is entirely zero. Then, rather than adding a zero to the end and filling the next values of each previous sequence, you should instead add a zero to the beginning of your sequence of zeros, then fill in the first values. In particular, here's what the third example history looks like when extrapolating back in time. So now, we have the 10 and 13, we compute 3, 3 and 3, 0, 0 and 2, 2, 2 and 2, 0. But then we add a 0 to the beginning, and then instead of adding to the right, we subtract. No.
Yeah.
It is
Yeah.
x plus...
I think you're... Yeah. I think your analysis is very good, though, that all... You know how you just added the last column? Now all you need to do is subtract the last column.
Well, is that right? I want to work this out with a more complete example. So this 2, how was this 2 computed? It was x plus 2 equals 0. It is 0 minus 2. This should have been a minus 2, but it isn't. So I'm confused. I am not doing the right equation. What is up here? It is 2 minus x is equal to 0.
So if you look at...
It's 2 minus x. It's the right-hand side minus the left-hand side is equal to 0. So 2 minus 0, so it is the one above minus the one below. That's what x is. And to reorder things to make it easier for me to read, it is this. So in general, what I want to do is this minus that, and this minus that, and this minus that, and this minus that. Yes. Go ahead, David.
So just based on your example, if we, on your previous... Oh, I can't actually... Oh yeah. So if we just take this one, minus this one, minus this one, minus this one. And put that in, we get...
Yep. Okay.
So we can... It's the same, similar principle to what you showed on the first one, right?
Yep. But with subtraction and going from the way up. So in general, this recursion relation will be a bit awkward for me to reason about, but I'll get there when I get there. And because this code is so fast, I will just copy and paste it below. And I guess I will comment it out. There you go. That's part 1 for you all.
Okay.
Because we will want to... I see something on Skype. Is that you, David?
It is, yeah. Unfortunately, you have to reshare the VS Code link. It's died. Thanks.
Of course. So we know that I is equal to 0. C, D, E, F, G, H, I. Okay. And we know that if the configuration is A, B, C, that's the formula. So we want to take the one below and subtract from the one above. Nope. Nope, I'm wrong again. We want to take the one above and subtract from the one below. So we want to do G is equal to H minus I. Let's see if I can convince myself that this is the case. G is A is equal to H, which is B, minus I, which is C. Okay, and then E is equal to F minus G. But we know that G is this. And C is equal to D minus E. E is that. And A is equal to B minus C. But we know that C is equal to that. So, in the end, we don't want to be subtracting on the way up, do we? How does this work out? A is equal to, so minus H plus I. Now let's pull in this subtraction. Minus F plus H minus I. Now let's pull in this subtraction and we get minus D plus F minus H plus I. So in summary, we want to keep alternating subtractions and additions on the way in. So we are going to see on the way in B, D, F, and H. B, D, F, and H. I is always equal to 0, so that's trivial. It doesn't really matter what we do there, but what matters is that we start by adding, then subtract, then add, then subtract, and so on. And so we start by adding, and that looks right. And I will have like a should subtract, which starts true. And if I should subtract, then that or that should subtract is equal to not should subtract. Okay. Now,
Wow.
for the real inputs.
Did it work for the test input?
Yep.
Nice.
Oh no. It's doing the loading thing. That's the right answer. You got 1 gold star. Finally. Yay. I have a gold star. I'm about to cry here. Oh my god. I got a gold star, people. Congratulations,
Well
everyone.
deserved. Well deserved. Well deserved. I'll have to be honest. I'm a little bit in the dark here because, yeah, just think internet-wise, connection-wise, it's not working very well for me. I can't really see everything, which is going on your screen that well, and the following and stuff. So I wonder if we should resume when we have better internet.
Well, we can do that. We can also try and work out something else. Like maybe if you turn off your camera, then you will get a better video stream.
Yeah, and also maybe I do kind of need you to be sharing the Skype window with me.
I can take care
And
of
I don't
that.
know if but yeah, I can try that. We can try that.
So And has it been a problem throughout the call or just now?
Just now, just for like, because since you've been sharing, basically.
Okay.
Okay, now I don't know why, but all of a sudden it seems to be a lot better. So,
Perfect.
so could you? So what you're doing here is, if you should subtract, you're alternating whether you should subtract.
Yeah.
Could you explain why?
Yes, it is. I worked on that example input. This.
Yeah.
In fact, I used the drawing from Advent of Code. So I used this drawing here, and I started replacing, or maybe not. Yes,
You
this
did
one. This one here. I started replacing this the two leftmost
Yeah.
columns with letters, and I used the rules of the problem to say that 10 minus 5 is equal to 5, but I had letters in every place. And then I expanded all the equations. So if I had like a minus b equals c and c is equal to something else, I would replace the c in the original equation. Until I got to a big long equation, but I noticed that there was a pattern of minus plus, minus plus, minus plus. And then I implemented that and it worked. Now, why does it have to be minus plus? I don't have an intuition for that. I just worked it out from the patterns I saw.
Yeah. Yeah. Okay. That makes sense. Yeah, I did see you working through that. I just didn't see all of the workings, but I guess that makes sense if you just worked it through and that's what it was in the end, and you just took it as, subtraction is an associative, so
Yep.
it's not going to work.
Yeah.
That makes sense.
And I'm sure that given the size of the examples here, I'm fairly sure that you could just do the brute force thing and expand everything following the rules of the problem.
Yeah. I mean, we are kind of doing brute force, aren't we?
Well, we are kind of being cute and not storing extra information we don't need. We are not storing previous lines, and we are computing on the way down. We are not computing on the way back up. As in...
Yeah,
we are being kind of cute. We are not being so naive.
No, it's true that we're not like using all the memory we need to. That's definitely true. But we're not like fundamentally changing the problem, I guess.
Yeah.
Yeah. Okay, shall I do day 10?
Yes.
All right, I'll be reading from your screen. So let's hope that the internet stays in its current form. I will reshare my VS Code.
Okay.
What do you think?
Yep. Yeah, what we learned is that whoever's driving needs to be the host of live share.
Yeah. Exactly. Okay. You know what? I'm actually going to invite you just directly rather than sharing a link. Oh no, I have to share a link. Okay, fine. I was just wondering, like, because if there's reconnection issues, you could, I just want to give you access. Really? But anyway. So, let's have a look. The feed is constantly freezing.
Yeah. That's too bad.
Yeah. That is too bad. But I feel like now it's probably fine.
Okay.
Okay. Let's have a read.
We are doing the best with the internet that we have.
Yeah. That's for sure.
Yeah. All right. Problem number 10. Pipe maze. Take it away, David.
You use the hang glider to ride the hot air from Desert Island all the way up to the floating metal island. This island is surprisingly cold, and there definitely aren't any thermals to glide on, so you leave your hang glider behind. You wander around for a while, but you don't find any people or animals. However, you do occasionally find signposts labeled Hot Springs, pointing in a seemingly consistent direction.
I'm going to one of those on Wednesday. Well, probably not out of a volcano, but it's going to be a hot spring.
in Gerais.
Yep.
Nice.
In Spain,
Um,
probably in Spain.
Oh, okay. Maybe you can find someone at the hot springs and ask them where the desert machine parts are made. The landscape here is alien. Even the flowers and trees are made of metal. As you stop to admire metal grass, you notice something metallic scurry away in your peripheral vision and jump into a big pipe. It didn't look like any animal you've ever seen. If you want to take a better look, you'll need to get ahead of it. Scanning the area, you discover that the entire field you're standing on is densely packed with pipes. It was hard to tell at first because they're the same metallic silver color as the ground. You make a quick sketch of all the surface pipes you can see, your puzzle input. The pipes are arranged into a two-dimensional grid of tiles. Vertical pipes connecting north and south. More graph theory. Horizontal pipe connecting east and west. 90-degree bends connecting north and east, etc., etc. Dot is ground. There is no pipe in this tile. S is the starting position. And that's that. Okay, based on the acoustics of the animal scurrying, you're confident the pipe that contains the animal is one large continuous pipe. For example, here is a square loop of pipe. All right. So what's F? F is a 90-degree bend connecting south and east. Where's S in that example?
Not yet. It will be here. It's just showing you the loop.
Okay. If the animal had entered the loop in the northwest corner, the sketch would instead look like this. Makes sense. In the above diagram, the S tile is still a 90-degree F bend. You can tell because of how the adjacent pipes connect to it. Yeah, I suppose that's true. Unfortunately, there are also many pipes that aren't connected to the loop. This sketch shows the same loop as above. Yeah. In the above diagram, you can still figure out which pipes form the main loop. They're the ones connected to S. Pipes those connect to, they're connected to S. Pipes those pipes connect to, pipes those pipes connect to, and so on. Every pipe in the main loop connects to its two neighbors, including S, which will have exactly two pipes connecting to it, and which is assumed to connect back to those two pipes. Here is a sketch that's a lot of pipes in one paragraph.
Yes.
Here is a sketch that contains a slightly more complex main loop. All right. Let's see. S is there. Now J is a 90-degree bend connecting north and west. Okay. And then that connects to there. I see. Yeah, you're tracing it nicely for us. Yeah. Okay, cool. They could have gone with more creative characters, I think.
I would have used Unicode, but I understand why not doing that is advantageous for programming languages that don't deal with Unicode all that well.
If you want to get out ahead of the animal, you should find the tile in the loop is the farthest from the starting position. If you want to get out ahead of the animal, you should find the tile in the loop that is farthest from the starting position. Because the animal is in the pipe, it doesn't make sense to measure this by direct distance. Instead, you need to find the tile that would take the longest number of steps along the loop to reach from the starting point, regardless of which way round the loop the animal went. In the first example, with the square loop, you can count the distance in each tile from the starting point, like so. 0, 1, 2, 3, 0, 1, 2, 3, 4. In this example, the farthest point from the starting is 4 steps away for first search. Here's the more complex loop again. Here are the distances for each tile on that loop. Okay, I'm just going to trust them on that. Find the single giant loop starting at S. How many steps along the loop does it take to get from the starting position to the point farthest from the starting position? Okay, let's have a look at the input.
I'll tell you one thing. We are starting here.
Yeah. Okay. Uh, all right. So this is what problem is this? Number
10.
10.
I have an idea.
Okay.
I think in the end, in the real input, there will be more than one loop. And we will not just find one loop. We will need to find all of them because we want to find the longest. You see what I mean?
Say that again. In the real input, there will not be just one loop.
Yeah.
So
in the examples,
we-
they have one big loop. But I think that in the real input, there will be, imagine like this. There is like, if you start here, then there is one loop, but there will also be another loop which is bigger.
Okay.
So I think
But
that
one-
in general, we
but-
will need to do an exhaustive search starting from the start and trying to fill in. Imagine that water is flowing in from the beginning, and we need to go through every possible place where the water goes so that we can visit every loop because we don't want to stop in the first. So we will do a breadth first search starting at the start, or a depth first search, it doesn't really matter. But anyway, because we will need to be exhaustive so that we can find the biggest loop. And while we are doing that, we might as well just keep the counter, because then when we find a loop, we store the number of steps we took to get there.
Yeah. It would be not. You know what would be nice would be to actually keep this string representation and output the distances in a string. Don't know if we'll need that, but so this thing about having multiple loops. Are you saying the loops could be connected?
Yeah.
Yeah. I mean, I was planning on it being exhaustive anyway, so perhaps we will do that anyway. I guess the assumption is, as long as it's connected to one loop, all we need to do is find the node which is furthest away.
Well, the
from
loop that
the
is
init.
furthest away is in order to determine that we
the
have
node.
found a loop, we need to go around the loop, right? That's the only
Yeah.
way to prove that it is connected. So the point that is furthest away is the length of the loop divided by 2.
Yeah. Yeah.
So we just need
That's
to
true.
find the length of the loop, and that we can do while detecting the loop.
Yeah.
Okay.
But why don't we? So does it not include? The thing is, if there's like I can't easily draw here, but say there's a loop, and then that loop has a little cul-de-sac going down the end of the loop. That still counts as part of the loop, right?
That's an interesting question. Could
Because we don't want to find the shortest loop. We want to find the node furthest away, which is connected to the loop, I think.
I would say that I would say this. It's not clear. But and because it is not clear, I suppose that will not be in the inputs. But I would say that if you find a cycle but it hasn't reached the start, that doesn't count. Because you could be running away from the animal and the animal would be running in your direction and you would meet in the middle. And that's no good, right? We are trying to run away from the animal. So I would say that if you find a cycle but it's not cycling back to the start, that doesn't count as a cycle, that's a dead path. We stop the search. You see what I mean?
Okay. I have an idea of how to do it.
Okay.
Which I think I will. Let's just try and implement, and then let's see if that works or not. But can you see? We need to first work out how to use these directions, which currently, I guess for each of these, there are two possible things that it can do, right?
The way I
can
like to
either
think
go-
about this is it's directional, as in if I get into an L from above, then I want a map that tells me that next I need to go to the right. And if I get from the L to from the right, I need another
Yeah.
map that tells me that now I need to go above.
Yeah, yeah. So perhaps we want something like, if it's on the left, then it will do -1, -1, like that. And if it's up, well, yeah. I find left and up easier than north, east, southwest. So if it's up, then it will be 1, 1. Does that make sense?
Not quite. If I am coming from below, in other words, I came because I was below this, and now I went up.
I'm going up.
I'm going
Yeah.
up. So now I would say that we just go to the right. I arrived at F, and now I go to the right.
Okay, yeah.
Like that.
And then if I'm going left,
Yeah.
okay.
Yeah.
I buy that.
And now I want to be cute and say, instead of the words left and up, I want to use the tuple that represents the movement we made to get here. So we went up to get here. So I want to see there 0, 1, if you know what I mean.
So if we go up, this will take us right.
Yeah.
And if we go left,
This will take
this
us
will take
down.
us down. I am going to translate these later because I find it easier to do the definitions with text. Is that
I
right?
agree.
So if I'm going, what is this, down? Then it will take me left. And then if I'm going right, it will take me up.
Yeah.
If I'm going left, it will take me up. And if I'm going down, it will take me right. And is that right? If I'm going up, it will take me left. If I'm going right, it will take me
I
down.
agree with that.
And then dot, what does that mean?
It's empty.
If I hit a dot. So it would just be like nothing,
Yeah.
right? And then this is if I'm going down, take me down. If I'm going up, it will take me up. And cool. See, Copilot is useful.
Glad to hear.
Let's just make this a little bit tidier. Okay. Now I just want to I'm probably going to have something like left, like that, for the directions. Now, the way I'm thinking about this is I'm going to do breadth first search, starting with the start as the...
Okay, just to make sure, line 161 means that the grid starts on the top left 0, 0, it grows to the right, and it grows to the bottom. So positive values of y go further down to next lines below.
So this should be. Oh yeah, this is wrong. We want to do row column. Modify the row and modify the column in that order. So that's generally how things work. So this should be 0 minus 1. Good catch.
No, I'm okay. I was okay with the other thing. I was just trying to make sure that we were on the same page. So now what you're saying is that the coordinates are given y, x, and
we're gonna work with row column. We're gonna work with row column. Row column's always easier to think about, especially when you have 2D arrays.
okay, so we are doing row column, and we are doing left is -1, right is 1, up is -1, and down is 1. Okay, I can get behind that.
So find the start node. Then we have our sort of open list of the start node, and we're going to do BFS until cycle. And then I guess for return the
Wait a second. When we say BFS, it implies bifurcation. But given the shapes of the pipes, there are no pipes that bifurcate. So we don't need BFS. We just need to, for every possible start in S, follow it through.
I think we need BFS because we do have always, when you're at the start node, you can always go out in 2 directions.
Well, you can start in 2 different directions, but once you start, there are no bifurcations along the way.
Well, that's true.
So we don't need BFS. BFS is too powerful for our problem.
I think BFS makes sense because it will also solve it will find the shortest cycle as well. Rather than depth first search, we could end up going down some cul-de-sacs and stuff.
No, I'm not talking about depth first search or even breadth first search. Because both breadth first search and depth first search imply bifurcation. It implies that at each point in your search, you may need to go to 2 different ways, or 2 or more different ways. In our problem, we don't have that.
Yeah.
Because the thing that I was thinking about this situation of maybe there is a cycle and another cycle that springs off of it, it's impossible because it implies that over here there is a bifurcation, and a bifurcation is not possible with the shapes of pipes we have.
Let's put the input here so we can talk about something more concretely. Because if I'm at the start node here, but I could go off in 4 directions. From each node, they're like, oh, there's not because we have pipes.
And there are no diagonal pipes. You cannot jump straight from S over here to this. So in S, you have to consider north, east, south, west, or up, down, right, left. And from there, we need to go. We just need to find a loop. We just need to follow the pipes and try and find a loop. We don't need breadth first search. We don't need recursion. We don't need a working list.
But I mean, okay, I'm just thinking, I mean, breadth first search would be easier for me to implement than something else. I'm trying to think what else I would do. I guess I would do depth first search where I just follow it, I just traverse it down.
Yeah. And you are calling it depth first search, but it is, I guess, a subcase of depth first search in which there will be no bifurcations along the way. Because in depth first search for real, you would do something recursive and complicated and keep a work list somehow, maybe using the recursion stack as your work list, but you would do something complicated. In this case, it's just a simple while loop. While my current position is different from S, follow the pipes through. And a dot means break, and F and J and L, you just look up here.
Yeah, okay. All right, I suppose. Yeah, I'll do that. that works for me. So I guess we just pick one direction, don't we? Wait, what if we have multiple directions though that we could go
We don't.
for the starting?
Oh, from the start point, yes. From the start point, we want to consider all up, down, right, left possibilities. And we know for a fact that one of these is, or at least one of these is redundant, because whatever is a cycle, it's gonna go, let's say, from the top and come back from the bottom, or something like that.
Okay, let's do it for one then, and then we can adapt it. I probably would feel more comfortable writing the breadth first search solution, but it's good to challenge myself. So I'm gonna.
It's interesting that
go
you are
ahead
more
with
comfortable
this.
writing the more complicated thing. Right?
Yeah, it's because I've written it a lot of times, I think.
Okay.
But yeah, so let's try. Um, Oh well, I guess I need to find the root node anyway.
Can we start by parsing, by just splitting on the new lines?
Oh yeah, we need to do that. Sorry. Line in input.split lines. We are going to want to. I guess we don't need an adjacency list this time. Instead, we can just work with a matrix.
Yeah, I would just do input.split lines, and that's my parsing, because then we can find the rows by indexing into that, and then we can find the we can index into the string. So this second split you are writing, strictly speaking, is superfluous, but it's all right.
Oh yeah, that's true.
And then you see how what you're doing is essentially just this.
Yeah.
Yep. Bonus points for the list comprehension.
Yeah, exactly.
Do we have to worry about extra spaces in the beginning and the end of the line? No, right?
Yeah,
I always
may as well.
stream everything, but and then I would want to do the dot strip here as well. And I did. Carry on.
Okay. So the start node, we need to find the node. Annoyingly, index throws in that looks right to me.
I'll take your
Yeah.
word for it.
Then Copilot's trying to read my instructions with the comments.
Cute.
Around. We're instead going to say while true. I guess it's going to be So the children is going to be, or for direction in directions. I think. Uh, um, something like that.
Let's see. You have a start node, which is that, okay. And then you're popping the start node.
And we're going through each direction
Ooh.
and checking each direction to see where we need to go, right?
And then directions. What is directions?
That's up, down, left, right.
When you say for direction in directions, you're getting the keys.
Yeah, so
Okay.
um,
So you're saying
I
that the
think it'd be
child.
clearer if a direction name direction in items, and then I can do something a bit cleaner.
Well, directions at direction name is just directions, so you could say this.
Yeah. Yeah, absolutely.
Okay. And then we assign to child, which we haven't seen yet. Are we doing a work list?
I think we are.
It feels like nodes is a work list.
It is, yeah. It's an open list. That's what I'm adding. That's where my brain is going.
Okay, I'm interested. I want to see where this goes. So we assign to child. What do we do next?
So we get the child, and then we need to work out if
You're here detecting a cycle using node in scene. If I understand correctly,
that's not going to help.
that is
That's not
unnecessary.
gonna help. Well, it's also not going to help because it's just going to be a character. So I need to. I'll need to think about that.
No,
This
hang on.
start-
I have the answer. If you find a cycle, you have found a cycle because you got back to the start. That is the only way you can get a cycle. You can just detect if node is equal to S.
Yeah, that's true. That is true. 100% true. Well, that's true, but also you could meet in the middle, right? There's two ways of doing it. You either go all the way back round, or you meet in the middle. So like you're traversing this thing. Do you see what I mean?
I think what you mean is impossible because there are no bifurcations. There is no kind of pipe that has three endings.
Not three endings, but you could meet in the middle of the loop.
I don't see how that would be. Can you draw it for me?
Well, if you're doing BFS, then it would happen, right?
No, I don't see that.
So I wish I could draw easily.
Excalidraw, maybe?
Yeah, we could definitely do Excalidraw, but yeah, I can share it in Excalidraw.
Okay. And look at this Scully draw. I'm
There's
pretty
also
sure
some,
that
like-
this is like us trying to work on some other problem.
I'm sure it is.
Okay.
I'm actually opening up a new one so that because I've got loads of crap on mine as well. Start session, copy link, send Skype. And 7. So if you have a starting point here, and then you start going in this direction
Hmm.
and this direction around the loop, eventually they'll come and meet together.
So that's the fundamental difference in our understanding. The way I see this problem is we start here. There are 4 ways we can go.
I know.
I will arbitrarily say that I want to start going up. So I'm going to go up, and I'm going to go around, and I'm going to go around, and I'm going to get nowhere. Okay, that's all right. Then I'm going to go right, and I'm going to go around, and I'm going to go around, and I'm going to go around, and I'm going to come left. All right, I found a cycle. Then I'm going to go down. And at this point, we know it's silly to go down, because if there was a cycle, it would have come back up north. But I can do it anyway. I can just go, and that's the end.
Yeah.
And,
Whereas I was thinking, like, traverse all of these. I guess my solution is actually, I might not find the longest cycle. I need to make sure that I explore everything.
well, you'll find the longest cycle because you're exploring every path.
Yeah, but I need to make sure that I don't break when I find a cycle. Whereas you, I mean, you could have two, it is possible to have 2 cycles, as we can see from my one over here, right?
Yes.
This does have 2 cycles, so we need to make sure that even on yours, as soon as you find a cycle, you might still have to find another cycle. So you need to find the longer one.
Yeah. So there are some special cases that are kind of cute, like if you have found a cycle that is left-right, if you know that the cycle starts on the left and ends on the right, then you are guaranteed to not have another cycle. You don't need to explore the other cycle, because if there was another cycle, it would need a pipe that crosses, and that's impossible. There is no pipe that is a cross like this. So by the topography of the situation here, the topology of the situation, that cannot happen. So you could excuse yourself from exploring the other 2, but we don't need to do that. We can just explore the other 2 and whatever.
Okay. Let me continue down this road, and then we'll rewrite it with probably your much simpler approach in a minute. So we get into, if the node is in the scene, then it's a cycle detected, and I guess we will have to store the distance as well. So we have this child, which is the new direction. What's the direction here, though? That's not right, is it? That's just the child character. And then, if it's equal to, well, what we need to do is get the, what's it called? Like, I guess, edges? Child 2 equals like child 0. Yeah, I guess edge, right? Edge is the oh, I've labeled directions twice here. I'm going to call it connections. So it'd be like connections at child. But we need to know whether we came from it from the left or the right. So that will be the direction name. Does that make sense?
Maybe.
So the direction name, yeah. Well, we need to get it right.
Well, no.
We just need to
it
get
doesn't
it
really make sense.
because-
At some point, you will have to look up something on the board, or yeah, what we call the board.
Oh yeah, so this should be board here.
Okay. Now that makes a bit more sense to me. Yeah. Yeah.
So this is the child character, and then we want to find out what the edge is, and then if edge is not none, then we need to add the well, I think first of all we need to add that we got to that edge. We need to add nodes.append something. Let me just say r equals. Let's make this a little bit easier to reason about. Now, is that actually correct, or am I just making this up? I think what we've done here is we're looking at something above, for example.
Are we back on Scalidraw?
Sorry?
Are we back on Scalidraw?
No.
Okay.
No. I'm just trying to work out whether this is correct. So I'm looking at all my directions. So I'm looking north, west, south, east, whatever. And I find so now I need to find that up above thing, and I look at that child, or maybe I should call it neighbor. I suppose it doesn't really matter. And I find if that neighbor has got edges.
Hmm.
And if it's got if it has an edge, because we've come to it from up or down or left or right, then we need to add I'm just wondering whether we actually need to move it through it. Each time we look at it, we need to do a distance. What I'm thinking is I'm sure this is wrong. It feels very wrong, but it would be so the edge does something like that. Directions, edge, and then we do you see where I'm going?
I'm trying to find the definition of offset. Offset is directions at edge. Okay.
Yeah, so here we're looking at a node. and then we're like, okay, find the neighbors of that node. So each of these neighbors is going to be either.
Well, once we have a node, it can only have one
One of
neighbor.
those.
Why do we have a for loop?
It has 4 neighbors. Each node has 4 neighbors.
No, well, once you get into a pipe from one direction, there is only one place you can get out of the pipe.
Yeah, well, no, but we're not in the pipe yet. We're just at a node.
A node is a pipe.
A node, yeah, it is a pipe. Yeah, that's kind of the issue. Is I'm thinking each node, but every node is an edge as well.
Can I attempt something?
Yeah, sure.
Okay. So I like our definition of a board, and I'm going to use our definition of a board, but I am not going to use the rest of the data structures we have so far.
Okay.
And I will use your definition of a start node, which I like. So I will have a current node that to begin with will be the start node. And I will have a current direction, which arbitrarily I'm gonna say I want to start by going up. Then I am going to loop while my current node is not an S. And I actually want to do a do while, so I'm gonna do a true here, and I'm gonna deal with the condition later. Then I am going to move. And what I call current node here are actually the coordinates of the node. So I guess I'm going to copy and paste your code, and I'm gonna rename some things to the way that I think makes sense in my head. So I like the board. And start node, I guess I will call this coordinate. And then I don't need that. And direction, like that. Now let's exercise this direction and go up. So I will take my core. No, do we have a switch case in Python?
No.
If direction is up, then my coordinate is equal to coordinate at 0 minus 1, coordinate at 1. I don't like 0 and 1. I will turn this into not a tuple, but an object. Do I have objects in Python?
Of course.
How do I spell them?
So you want to have a. How do you want to be able to do it? You want to say like row column?
I want to be able to say coordinate dot row.
Yeah. Okay. So I'm going to import from data classes. Import data class, and we'll just define this up here as at data class.
Jeez, no. Forget about that. I take it back.
That's it.
No. That's terrible. No. I had to declare types. No. I will go with the coordinates. That's all right by me.
But the other thing is, you could just do a dictionary, right? You could just do like you might prefer that.
Oh, that's perfect.
Like that?
Thank you. That's what I call an object in JavaScript, and that's much better.
Okay,
thank you.
Fine.
That's what I want. So, row and column, and over here, my row and column. Do I have to put it in brackets and in parentheses, or does this syntax work? Like in JavaScript.
Yeah, that works.
Okay. So now I will do this 4 times. I will add. Do I have else It's Elif.
It's Elif.
Okay, and then right, and then down, and then left. If I'm going right, then I will change the column. If I'm going down, it's a plus, and if I'm going left, it's a minus, like so.
Yeah.
Then I am in a new coordinate. In that coordinate, it may make me change directions. So, if my board at coordinate column row, I have a typo, at coordinate column, if that is equal to something, and my direction is something. So if that's the case, then I will want to switch directions, and then my direction will be something. Else, so for 1, 2, 3, 4, 5, 6, so 12 in total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if my direction is, I'm currently going, I guess I will copy this for reference. If I am going, I'll start with the easy pipes. I'm going down, and my current tile is a pipe. I will continue to go down. If I'm going up and I see one of those, I will continue to go up. If I'm going right and I see one of those, I will continue to go right. And if I'm going left and I see one of those, I will continue to go left. Now, if I am going up and I see one of those, I will start going right. If I am going left and I see one of those, I will now go down. If I am going right and I find one of those, I will now go up. And if I'm going down and I see one of those, I will now go left. If I am going down and I see one of those, I will now go right. And if I am going left and I see one of those, I will now go up. If I am going right and I see one of those, I will now go down. And if I'm going up and I see one of those, I will now go left. And this is important, if none of those apply, then break. I have found a dot, I have found a pipe that I shouldn't, something happened. Oh, but there is one extra condition. After I have applied all of these situations, if I found an S, there is something special here.
You want to pass or you want to break?
I want to do something. I don't know what it is yet. I know that
Pass is nice.
when I arrive here, I want to break. That I know, because it means that I haven't found anything interesting after having seen this.
Mm-hmm.
And I guess I can give this a name to avoid the long repetition here. So I'll call this my node, or my pipe even.
Oh, pipe's a nice name. I guess you can replace that in all the places.
Then when I arrive here, I will want to do something. I will want to count how many steps I took, which will be the cycle length. Which I will add as the first step here. And I will want to do something with the cycle length. Well, there will be at some point the maximum cycle length. So I will say that if, and I will want to break in the end, if, or not even, my maximum cycle length is equal to mathmax.
You don't need math.
Thank you. Great. Something like that. Now, naturally, I don't want to do this only for up. So for direction in up and right and down and left. There. And I do want to deal with the cases in which I go over the board. So if my coordinate row is less than 0, or my coordinate column is less than 0, or my coordinate row is greater than or equal to my, well, the number of rows is the number of board length, or my coordinate column is greater than or equal my board at 0 length. If any of those break, I have gone overboard. And this indexing would even fail, perhaps.
Yeah.
All right, so what I'm doing essentially is just simulation. I am just doing the turtle. Do you know that programming language that is a turtle and you draw with the turtle?
Yes.
I implemented
I've heard of
I
it.
implemented that. Then for the output, we print the maximum cycle length divided by 2. Yikes. This code is, it looks awful. This cycle length should be in
No, I think-
here.
I guess if you'd use the dictionary, this would like amount to one line.
Yeah, it would be expressed more shortly for sure, but that's how it panned out for me.
Well, I guess both this line and that line, and all of these lines would, but it's maybe a lot simpler to reason about.
Is there anything else that stands out to me as obviously wrong?
Yeah, so I guess the core thing is that you are keeping the direction. The direction is kind of the node, in a way, that you're mutating. Each time you change the direction,
Yeah.
you update the coordinate.
Yeah, if you want to think about this as a state machine, my direction is my states, and the pipes are the arrows between the states. But I don't want to think about it that way. Now, I am reviewing real quick the mappings here. Go right. From left, I go up. If I go from the right, I go down. And if I go from the up, I go left. Yeah, I believe in all of this, and I'm happy about this. So, tell me, does this make sense to you?
100%. 100%.
Excellent.
Yeah, nicely done. Yeah.
Now, does it work?
Let's find out. I guess. Oh, by the way, yeah, I don't think you can do dot row. You have to do like row like that.
Okay, I can take care of that.
You want to do all the renames? I could do that as well. Don't mind.
I am doing it. Okay.
Yeah, you did it correctly here. Cool. I'm just thinking whether. Yeah, it wouldn't be much easier to read as a if you use the graphs, to be honest. It kind of makes it harder.
Oh,
Okay.
whoop, whoop, whoop. Not that it matters because there is a break in the end, but that's my intent.
Yeah, yeah.
Because essentially, in fact, I'm gonna do something real quick that doesn't affect anything, but I'm first looking at the pipe. Yeah, I'm first looking at the pipe in all cases, and then the direction. And then you could easily turn this into a data structure, but I won't.
Yeah. Yeah.
Okay, now I'm happy. Can you run this? Perhaps we need to comment some stuff above and put the example input is already in place, but
Type error. Tuple indices must be integers or slices, not string. In which is in the direction, in the coordinate column. Yeah, coordinate here is not a coordinate. You have to do the.
correct. Yep, I can take care of that. Oh, you're already taking care of it. Thank you very much.
No, I didn't do that right.
Yikes.
Now I bet you. Now do you wish you had the class?
No way.
Okay.
Does it work?
All right. Let's see. It says 1. 1 is the answer. So I guess not.
The answer should have been what is our example input? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It should have been 7.
It's breaking on the first. I think you just want to do continue, don't you? Yeah.
Absolutely not. Because this is when we have gone over the edges of the board.
Oh no, yeah. Yeah. I'm just thinking, so it's exiting on the first iteration every time.
No, the problem may be that our coordinate is never reset. So here is to begin, but when we are doing the up, down, blah, 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 we need to say here that our coordinate is equal to the so-called Start coordinate. That's one issue.
Yeah.
At least. There may be more, but can you run
Makes
it again?
sense.
Still 1.
Yep. Yeah, you got 8.
Maybe
got
8 was the by hand. I did it wrong. Let's see. Yep, 8 was the right answer, and I did it by hand, and I did it wrong. So we are ready to rumble. Let's run off the inputs.
Okay,
Right? Can I paste it in?
let's do it. Well, you have to paste yours. I think?
Yep. Can I do that?
Yeah.
Okay.
You have to. Yeah. Yeah. Paste it in.
I am pasting it in, people.
Yeah.
I pasted it in. And 6886 is the answer for my input?
No. That's mine. Wait. Hold on.
We have some live
Maybe I think there's an issue.
we have some live share explosion here.
Oh yeah, you still got this one commented. That's the issue. 6786 is the answer for your input.
Thank you. And not only that, but it also is the right answer. Good job. Good job.
Hey, good job. Yeah.
All right.
That was beautiful.
You quickly reach the farthest point of the loop, but the animal never emerges. Maybe its nest is within the area enclosed by the loop? To determine whether it's even worth taking the time to search for such a nest, you should calculate how many tiles are contained within the loop. For example, this. The above loop encloses merely 4 tiles. 1, 2, 3, and 4. The 2 pairs of dots in the southeast and southwest marked I below. Yes, this one. The middle tiles, blah, 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 are not in the loop. Yeah. In fact, there doesn't even need to be a full tile path to the outside for tiles to count as outside the loop. Squeezing between 2 pipes is also allowed. Here, I is still within the loop and O is still outside the loop. Okay. In the above examples, 4 tiles are enclosed by the loop. Yeah. Here's a larger example.
Why aren't the zeros enclosed by the loop?
Because I guess the best way for me to reason about this is actually the algorithm for us to compute the thing. Think about it this way. You start here, you go to the right,
I see it.
and you keep looking to your
Yeah,
right,
zeros.
and everything you see between where you are and the other pipe coming back is what you count as inside the loop.
Yeah, I now. Yeah, I can now see it at least. It's on the outside of the loop, following it through.
In both of the above examples, 4 tiles are enclosed by the loop. Here is a larger example that I barely want to look at. The above sketch has many random bits of ground, some of which are in the loop and some of which are outside. And in this larger example, there are 8 inside. Any tile that isn't part of the main loop can count as being enclosed by the loop. Any tile that isn't part of the main loop can count as being enclosed by the loop. Okay, so we don't need to just merely look at dots. It could be other stray pipes. Coming back to my Scully draw for a moment, and not to any Scully draw, but the one I had before I enclosed the things. So this Scully draw. If we were to count the area inside this loop, it doesn't matter if there is some other pipes in here. They are counted as space as well. That's what I understand. Here's another example with many bits of junk pipe lying around that aren't connected to the main loop at all. Here are just the tiles that are enclosed by loop marked with I. And indeed, there were some pipes here that turned into eyes.
In this last example, 10 tiles are enclosed by the loop. Figure out whether you have time to search for the nearest nest by calculating the area within the loop. How many tiles are enclosed by the loop?
Okay, it's quite complex, but my thinking would be to, again, breadth first search, but fill the space inside the loop until you reach the boundaries of the loop,
I like
and
that.
keep in memory a scene of all of the nodes in the path.
I like that.
Yeah. Again, it doesn't depth first search or breadth first search doesn't really matter here. The nice thing is it's very easy to keep the path of the maximum cycle.
Yeah, my
with the
simulation here
algorithm.
is really amendable to that. So coming
Yeah.
back to this code, I am going to copy and paste so that I can modify without breaking. But I will keep the parsing. Or maybe not even that. I will just add stuff for part 2 here. So here are the coordinates. No, not here.
Yeah. Yeah.
Not even here.
Shouldn't we call it the path in here?
Yeah, go ahead. Drive.
And then we yeah.
Yeah.
And then when we get to where is it? Like that?
Well, we also want to append that again because we want the S to be in the path, or at least I think it would. I would like that. So it's a closed loop.
S is in the path?
No, it isn't because we have just changed the coordinate in this block, right?
Oh, I see. But isn't it just a set? So it will, since it's starting there. Like, I was thinking actually that this is a set. And we will just add it.
As you wish.
Because that will make it easier to check if the coordinate is in the path or not.
Okay.
And then, do you agree with doing BFS for this second part?
Yeah, there's just one thing that I still don't get. The path contains every coordinate we have been on.
Yeah.
Except for the last. Oh, because that's
No,
when we
but
found ourselves, so we don't need to include it again. Now I see it.
Yeah. Yeah.
Cute. Does it work?
Uh,
For the example input, do we get the right path?
Let's have a look. And we can... I'm not sure. Need to just uncomment that. Okay.
And can we change line 337 to read
type
set
error
instead of
on-
list? Because it's not really a list. Or is it?
Oh, yeah, sorry, that shouldn't be.
Okay.
Unhashable type dict path.add coordinate. Yeah, this is the issue with using the dictionary now.
But we've painted ourselves in
That's
that
fine.
corner. Let's use a list instead of a set.
No, that's fine. We can just do this.
Yeah, we can, but then we changed representations in the middle of the program, which is wonky. No, let's have a list instead of a set.
How are we going to check if it's inside then?
Index off.
Yeah, then it's going to be like n squared and be really slow.
Yeah, but this program is not a huge input. The problem here is the algorithm, not the size.
Okay. And yeah, you mean the size of the path? Yeah.
Yeah.
Okay, append coordinate. That's all we need to do. Okay. And then on to the second part, which is
Did you confirm that these outputs make sense?
no, I just printed them.
Okay, I want to confirm that they make sense. So we are starting here, and we are going to the right. Nope, we are going to we are going down. We are going down again. Then we are going to the right. Then we are going up, and yeah. Okay,
Yeah. And the last one is 2-1, so makes sense.
makes sense. Whoops.
So, how do we know if it's inside or outside?
Well, that's a great question, and we could try and be cute about it. For instance, if in the beginning we are going down and in the end we are coming from the right, then we know that our area is going to be to the right of the block that is down.
That's true.
Or
we could
calculate the inside and the outside, and on the outside we will know that we are on the outside because we will reach one of the walls of the...
Yeah, that's
the
what I
puzzle.
was thinking. That's what I was thinking. Should we try that? The hit at the edge of the board one?
I'm fine with that.
Okay. So I guess we'll start with this same idea. Then if coordinate equals start coordinate, while true, I mean, we're going to have to do the same traversal, more or less. No, we're not actually at all. While true, if so next coordinate equals coordinate I guess it's this. So that's the next coordinate. And if it's outside the board, then break. And we will set it to is inside, is outside. Otherwise, oh, there's going to be a much better way of doing this as well. We should do the directions inside. Okay, we'll get there. So, this is the next coordinate. If it's outside, then we break. Otherwise, we get the... we don't care about the character, actually. And we just need to count.
Yep.
And then for direction in in up, right, down, left. We want to I guess we need this working list unless we have a recursive thing. The issue is that the open list yeah, that should work. That should work. So this is just like while we have an open list, then we want to ping off the current coordinate and then add the direction to it, right?
Mm-hmm.
And then if the next coordinate is out, then we're broken, and then we need to break and set is outside to true. And then for each direction,
I think I had a breakthrough. I don't want to interrupt your thought, but when you finish, I think I have a breakthrough.
we need to add the next coordinate. Oh, this is horrible. I'm doing something stupid here. I shouldn't be doing this.
So maybe
Oh no, we do need to do that.
maybe you will want to hear me, because I think it will make your idea simpler.
Yeah. Okay, yeah, go on. I'm gonna definitely rewrite this when we finish at some point, and yeah.
Why? Is there something that we
freezing.
are like? Are we doing something that
No,
you
but
don't agree with?
No, we're not, but I'm freezing a little bit in my mind, and I feel like this is something that I'm capable of doing. but
Absolutely. We are doing it.
I'm just going very slow. It's just coming to me very slowly right now.
Yeah, no. So think about this idea that I had, which I think will be kind of fun. We are trying to find the area inside, just these parts, right?
Yeah.
But we know for sure what is the area occupied by the pipe itself, because that is simply the length of our path, right?
Right.
So how about, instead of trying to compute this area, which can be a bit tricky because of these pipes that are narrow, and you have to squeeze between them, and you have to go and find these other dots, that is a bit tricky. And I was trying to think my way through that, and I was like, I don't like this, because I have to squeeze between the pipes, and there is even this other issue of, am I inside or outside the area? Are these dots inside or outside? How about we sidestep all this by computing not the area inside the pipes, but the area of the pipes and inside the pipes. The difference being that then we would compute this as inside as well, and that would be inside as well, but this would not. So we would just be doing, starting from the start, we would be doing your favorite, a breadth first search, and we would be keeping the boundary. So we would go in just the 4 cardinal directions. We don't need to do in the diagonals, because there isn't a way for you to create a diagonal path for the water to flow through, but we are going to flood this area. So starting from the start, you go north, you go top, right, bottom, and left. And then you recurse. So from here, for instance, you go up and right and bottom and left. Oh, but I have already seen this one, so don't go where you have already seen. And keep doing that. And anytime you find, for instance, if you're here, you go up, you go right, you go down. Oops, stop. That's outside. And then you keep doing that. And eventually you're going to...
Wait, how do you know it's outside?
Well, you know it's outside because it is beyond one of the edges.
Oh yeah, I see.
And then you're going to flood all this area with water, and then you subtract the area occupied by the pipes, which is, again is the length of the path, and Bob's your uncle. You don't have to think if you're inside or outside. You don't have to think of squeezing between pipes, none of that. It's much, much simpler.
Yeah. It's true. The way that I was thinking of it was I was just going to grow out from the starting point, but that's actually... I actually need to grow out from all the coordinates on the list. And then
No, you can start. You can start from the start. You can start from the start. Start from a single point and flood everything with water. And the coordinates will help you not overfill.
Yeah, and then just take away that. Yeah.
And yeah,
Yeah, that works.
And you know that here's how you know whether you should continue filling or not, okay? Suppose you're here, and suppose you're going to the north. Then that's easy enough. There is another pipe there, and you're going to the south. That's easy enough. There is another pipe there. So you will just find literally these coordinates in our path. Easy peasy. Then going to the left and going to the right, that's not so easy. How do you know that you should not fill? You shouldn't continue going left, but you should continue going right. Well, what I think is the case is that you should continue going right because there is another coordinate to your right. And not only that, there is an odd number of coordinates to your right, but this other part is kind of just an extra bonus property of this situation.
Yeah, because it's possible when you're on this other one, the one that you were selecting. Select that one again. Now select the other one, the one to the right of it. Yeah, because when you look to the right of that one, you're like, oh, there's an even number.
Yeah.
But there is one. So I can't fill.
Yeah. So in this one, you shouldn't go to the right. Alternatively,
but is there ever...
alternatively, instead of being smart about odd and even, you could just see, okay, I am going to visit this guy, and I'm visiting this guy because I'm going to the right. So you will continue visiting it, and then you continue visiting it, and then you continue visiting this, and then when you're here, you say, okay, I'm going to the right. Oh no, forget what I just said. You were going to say something that was probably more smart than this.
I was going to say, wouldn't it be simpler if we added all of the... Like, we are going to traverse all of the nodes, like in the map, 100%, right? Just take that as granted. We're going to visit every node. And we just add them all to the open list of the nodes that we need to traverse. And then we just breadth first search or depth first search, whatever, just try and fill it with water as much as possible. And then we don't break, we just mark all the nodes as seen. And then at the end, we've just kept track of whether we hit the edge of the board or not.
Ooh.
And if we hit the edge of the board, then it's not part of the sum.
That is brilliant. That is brilliant. Okay, I'm going to combine your idea with my idea, and I think we'll find a way that is very straightforward to solve this. Your idea of just taking for granted that we need to visit every point of the board, and then my idea of like wherever you are, if there is an odd number of pipes to your left, your right, your top and your bottom, then you are inside. And if there is an even number of pipes either to your left or right or top or bottom, then you're outside. Combine these two ideas and the algorithm is simply traverse every traverse every point, not every dot, but every coordinate, every character. Traverse
Cell,
traverse every cell, and for every cell, count the number of pipes you see to your left, to your right, to your top, and to your bottom. If any of these are even, you are out. If any of these are odd, you are in. And when you are on top of the pipe itself, you are out. And that's that.
Yeah, I find the I find the left, right, odd, even thing a little bit hard to think about. I'm going to paste in an example and see if I can break what you've said. I feel like it's I'm doing it in here. No, I want the example they gave with the loops. Where can I find that? Okay, down here. So I'm wondering if you could turn a very sharp corner. Like, say, for example, no. This is the tightest corner you can turn is something like this, isn't it?
Yes.
How do I do that? And that means that you're guaranteed to have two coordinates whenever you look left or right of here. So that's why it works. That's why it works. Because you could never have something dangling off the end, which is like this.
Because it is a cycle.
Yeah. Okay.
Yeah, I'm sure that some mathematician out there will be like, yes, there is a property that every convex area in any point, if there is a number of, but yeah, I think the intuition is there.
Okay. Do you want to drive?
I can. So we will be counting an area that starts at 0. Then for every row in port, will this give me the index or the row in and of itself? Because I want the index.
No, that would just give you the
So
what I would do is this, and
which one of these two is the coordinate? R or row?
R is the index, and row is the actual row.
Ah, I see. And then C is the index, and col is the actual cell, let's say. So, if row R column C is in our, how do we call that now?
Yeah, I don't think we're going to be able to do in, because it's not going to be a hashable type. So I think it's better if we'll have to define a function probably.
Well, how do we represent the maximum cycle path? What is the data structure for this? It's a list.
It's an array.
It's an array. And we are putting in the array what I call objects in
Dictionaries.
Dictionaries, okay. So it's an array of dictionaries. So we are interested in finding this dictionary in this array. Do you know how to do that?
Yeah, you just loop through it. I mean, it's saying that. I don't think that's true, though. Let's try it. It might work. You can just do try it in, and I'll try it in the terminal.
So, yeah, if I am on top of the pipe, then continue.
Yeah, okay, that works. You can just do in.
Great.
The other way around, though.
Okay. Cool. So if I am on top of the pipe, I don't want to count. If I am not on top of the pipe, then I want to count how many pipes I see to the right and bottom and left and up. So I want to go for I. And I'm going to type this in English and you're going to correct the syntax for me, please. So, no.
Python's basically English.
But I'm...
That's what Copilot's for, by the way. Write it as a comment. Write it as a comment and let's see.
Like that, okay. So what I want is for... I will go to the right. So for row, for R banana, from R to board, I'm not going to the right, I'm going to the, oh, geez Louise, it's complicated. R and C are not good for my head. I prefer X and Y. But in any case, I want to go to the right. So for C banana, which I don't know how to call that yet, from C+1 to board at R lane, not inclusive.
Okay.
Well, this one is inclusive.
That's what it says.
Okay. And our C banana is... It might as well just be C for what it's worth.
I mean, you could call it _C to represent like C prime.
Okay.
It's not beautiful, but...
In the range of C+1 and length of the board R. If the board at that position is equal to that, then area +1, else break. Well, no, I don't want to break.
And also, I guess you don't want dot, do you?
Yeah, I don't want dot there, no. I don't want this condition at all, in fact. Because what I want is to count the pipes I have seen along the way, so pipes count. And I will do some condition and say pipes count plus equals 1. And the condition is that I see a pipe. So in order to see a pipe, I will see something like this. The problem is, if I am the problem is, let's go to Scholar Draw. The problem is that I may be here. How do I draw? There. I may be here on this dot and I'm considering whether it is part of the inside area or not, and my pipe may go around like so. And then I will start counting all of these intermediate pipes which I don't care about. right? How do I want to count this? When I'm going to the right, I only care about pipes. The parentheses. I care about, or I guess essentially I don't care about lines, because that's the only thing that could distract me. Yep. So, and blah blah blah, not in, or it just isn't a line. That's the only thing that I don't want to have. And my syntax is wrong. Can you please fix me? Or JavaScript. Thanks. I think I believe in that.
So what? Repeat this. So if it's in the maximum cycle path,
therefore it is one of the
and-
pipes.
yeah, if it's one of the pipes, and it's not one of those, if it's not a left-right guy,
Why does Scarlet Draw not have a command Z? Cannot undo.
oh, it should do.
Nope. Once it's there, it's there.
Oh,
It,
I think that might be an issue with the collaboration side. But it generally works. But maybe not for live collab. Try again.
yeah, no, I cannot undo. Now I can undo, but I cannot redo. All right, so no, I'm wrong. It's not simply that. I don't care about lines. When I'm going to the right, I don't care about lines. This is gonna get complicated now. Because I do see one turn here and one turn there, and yet I am inside. So I guess
Doesn't it make?
I simply don't care about pipes and I don't care about J's. That's all. And then if my pipes count is even, then continue. And just like that, I will challenge the right, I will challenge the down, I will challenge the left, I will challenge the up. And then if everything works in the end, then I will finally say area plus 1.
I see. Yeah. Wow, that's gonna be expensive.
Yes, it will. So I'm gonna start by going up. I always like to go up. I like to do the CSS thing of up, right, down, left. So I will now change the rows. And it will go, since I'm going up, it will go from row -1 down to, or maybe I will go from 0 up to row -1. No, just to row, because the range is not inclusive. Then if this row and this column in, and it's not the case that I have one of those or one of, I'm now dealing with the case where I am here, for instance, and I don't want an F. And then pipes count, and so on.
What about a left turn? Is there not a scenario where you need to worry about that?
No, that's the problem. I'm trying to deduplicate because every time that I see a bunch of vertical lines here, it means that I will see, for sure, one of these turns and another one of those turns. Or I guess there is one extra case. There is one extra case because the area could instead be going... Erase doesn't work like I want, and undo doesn't work like I want. It's tragic. From the top, people. From the top. So, it may be the case that I have this. And I'm going to the right. It may be the case that I have this. And I'm going to the right. No, this is not the opposite of that. I don't think I can draw the opposite of that like that. No, no, no. The opposite of that is this. Okay, now I got the opposite of that. So here, I want to, let's say, take this in account and not that. So I will get us a green marker here, a red one there. And in this case, I will want to take in account, let's say, this and not that. Arbitrarily, right? You could just pick the reds and ignore the greens and it would be the same. But in this case, so I do want to count my Fs and I want to ignore my Js. So as I am going to the right, I want to ignore my J's. And I do.
Yeah.
When I'm going to the right, I want to get my L's, but I want to ignore my 7s. There. Now, when I'm going up,
I'm just thinking, Leandro. Is it not much simpler to just count the space, the negative space, and then deduct it from the total space? Like, just my initial thought was like, just fill the water as much as you can in every cell, and then you just either decide to keep that area or not keep that area based on whether you hit the edges or not.
That is a nice idea as well. It's probably even more efficient. The problem with that is that you have to feel but not count when you see these narrow pipes. Because you do want to, so suppose you start at the start.
Yeah.
You have to fill in this area without counting to reach here. And that is the problem that I was puzzling out when I started with this other approach.
Yeah. So there are some things which won't reach the edge, but are outside. That's the issue.
Yeah.
That's not a good. It's not a good enough check to see if it reaches the edge.
Yeah.
Unfortunately, because you can have it flush. Yeah. Sorry. Keep going.
I'm going to work out now the case in which I'm going up. I want to count my L's. I want to ignore my 7s. So when going up, which is this case, I will want to ignore my 7s. And similarly, I will want to, I have another case. I guess I will have to draw each and every one of these to be able to figure this out. I have my square. I have my area, which looks like that. And I will want to ignore this, which is an F. Then I'm going down now, so it's gonna be more similar to this. And I will want to go from r+1 down to the length of the board. And I made a mistake here, which I need to fix there as well. And here I want to discard the same. I will just discard the same because the problem is symmetric. Hooray, I don't have to work out 4 cases, just 2. And then for the C's, I will go from 0 to C is what I mean. From 0 to C. Nope, this is wrong. From 0 to, I'm going down, so no. I want to go down to C. Yeah, that is right.
You're going down?
Yeah. I'm going down, but I'm going from the top of the board to make this range easier to read.
If you're going down in rows, no?
Oh, geez. I hate this. I'm going to the left, is what I'm doing. I'm going to the left.
Okay.
Thanks.
Yeah.
And I ignore the same ones. And then in the end, I print my area. So let's review. What do we have here? I have an enumeration. I have row, which I only use here, and I have col, which I don't use at all, but that's all right. Then if I am inside the pipe, continue. If I am not inside the pipe, then I will check the pipe's count. I'm going up, so I'm going from 0 down to R. And I'm indexing into the right thing. Then it's not the case that this is going to count the dots. So I should add the dots. Wait, what? No. That is just completely incorrect. Because I'm counting a lot of junk here. No, I don't want to look into the board. I want to look into my cycle path. Yeah, I want to look into my cycle path. So there is another condition I'm missing. Or is there? Isn't this the condition that I'm already checking? Yes, that's the condition that I'm already checking.
Yeah.
I'm checking
It's
that
both
I'm
those
part
things.
of that path, and it's not the case that it's one of those that I wish to ignore. Then pipes count +1. And if it's all
Can you do
even-
this with list comprehensions, though? I'm joking.
I am in pain here.
Yeah.
Then print the area. Okay. Let's run this for the example input. And I should get a number 4 in the terminal.
I think, is that my code which is failing? Yeah, I think it's mine. It's fine. I'm just gonna delete it. I've taken a copy anyway. I can always implement it later.
Seems like my response is the number 1.
I need to pee real quick, Leandro. 1 sec.
So now what I'm gonna do is to print the coordinate that we are thinking is inside. Like so. And we think that 2, 2 is inside. Wait a second, that's not even inside, is it? That's 0, 1, 2. And 0, 1, 2. So that is 2, 2. Ah, we are working with a different input, and this answer is probably correct for this input. But for the example input here, then the answer should be 4. And the answer is 2. We are taking in account 6, 3, and 6, 7. So that's 0, 1, 2, 3, 4, 5, 6. And 0, 1, 2, 3. So that guy is correct. And I bet that this is going to be 7. Let's see. 0, 1, 2, 3, 4, 5, 6, 7. Ooh. We have a simple error of off by 1 because the logic seems to hold. Yeah. There is a simple off by 1 mistake here somewhere. Or is there? In this one, we are counting the L and we are ignoring the F. So when going up, count L's, ignore F's. When going up, ignore F's. When going up, count J's, ignore 7's. Ignore 7's. Great. Then, well, wait a second. Yeah, ignore 7's. Then there must be an off by 1 mistake on the ranges, maybe? Yeah. I'm thinking we are blaming the ranges here. For instance, this length, I don't know, I want to think about this from the top. Does this range make sense? If I want to go up, I want to go from 0 down to R. Who is R? It is the current coordinate that we are looking in.
That does make sense.
That does make sense. Then I'm going to the right. I'm taking my column plus 1 and going to the length of one row. And that's not inclusive, that's right. Then I'm going down. I'm going from R plus 1 to the length of the board, which is not inclusive, so that's all right. And then I'm going left from 0 to C. Okay, so my ranges are correct.
Yeah. Are you properly using always like underscore R, underscore C? It's possible that you're not referencing the right, you know, the C prime, the one in the range correctly.
I'm checking that right now. So I'm using the row here and I'm using the row there, and that's all right. Then here I am using the column here and the column there, and that's all right. And then I'm using the row here, and I copy and pasted this code, and I copy and pasted that code as well. So that should be working.
Yeah.
So let's run this again. We are only counting 6.3 and 6.7 as correct. Let's mark them here. So I'll do this exercise again. 0, 1, 2, 3, 4, 5, 6. And then 0, 1, 2, 3. So this is being counted. I am putting some hearts where we are counting. Hearts are implemented in this font and they don't stand out as much. So I will do this emoji. So it stands out better. But then this emoji isn't implemented, so the grid breaks. I guess I will go with the heart then. And then 6, 7 is being counted. So 0, 1, 2, 3, 4, 5, 6, 7. This one is being counted. And we are missing this.
Do you need to count self sometimes?
Hmm.
I'm just wondering if you're not counting the element that you're checking. Or you're only ever counting. Yeah.
Well, I see a problem already in my logic. My problem being the S. In this case, it doesn't matter, but in general, the S may work as a
Yeah.
7, may work as an F, may work as a J, may work as an L, and my logic does not take that in account.
Yeah, you can just add S to all of those.
That's
I guess
not the
that's fine.
case, however.
Oh.
Because when the S is acting as a 7, it's not
sometimes.
acting as an F.
I guess you can rewrite it,
Yeah.
but it's not the only issue with it.
Yeah, so there are two issues.
I keep thinking there's got to be a simpler, flood fill algorithm here, but then using the counts, but maybe not.
Well, the simple flood algorithm, as long as you do the trick of flooding the pipes as well, and then subtracting the pipes in the end, that one is straightforward.
Yeah.
Perhaps even more so than my janky solution here.
Yeah. If it is straightforward, then yeah, that's what I'm going to try and implement when I've had a bit of more time to sleep. Yes. But I still think it's not that easy to implement flood fill, just because they can be flush, and you need to work out if you're going the right direction or not when you're filling. I don't think it's that simple.
Well, maybe when we store the path, we could store not only the place, but also how we got there. For instance, if you got here by going to the right, then you should look to your right and not to your left, or you should look down but not up.
But that's not necessarily true. The loop could be the other direction.
Yeah.
How do you...
Well,
you have...
we are always starting to find the loop from the top. So that will give you some... If you go from the top and arrive at the left, or if you arrive at the bottom, or if you arrive at the right, then there will be different sections of the plane that could be part of this or not. But, okay, issue 1 is that S may work as different things. Issue 2 is an off by 1 somewhere.
Yeah. I can understand that you would say off by 1. And it doesn't seem to be the ranges.
Let's work on this example again.
Could it be the things that you're not counting? I guess why don't you print all of the characters as you're going, and then find out, oh, this one should have been counted.
I think it would be more straightforward for me to just try and work out why this didn't work by running the code in our heads. So
Okay.
I'll put this here, and I think I recovered the example as it should have been.
Yeah.
And then when I am here, this one, and I'm going up, I will find 1, this I will ignore, 2, and then that's the problem. I'm finding 1 and 2.
Does the count not work?
Yeah.
But
Perhaps
yeah, it was-
perhaps this whole idea of odd and even doesn't hold.
Yeah, that was
But it does, doesn't it? It does. It does. It does.
Okay,
Anywhere
okay.
you are, you will see an odd number of walls to your left and to your right. Because if you see an even number of walls, you're outside.
Yeah, I guess maybe it's the like ignoring things.
Yeah.
Which is not. Do you just want to ignore just the flat ones rather than you maybe still take into account the corners?
Well, maybe. Let's see the example I drew in Scholar Draw. From the first one. No. It's not as simple as that. I don't want to take all letters into account.
I'm gonna have to head off relatively soon, Leandro. I'm
Yeah,
sorry.
I'm dying here. I want this to end. I'm in pain.
I understand. Yeah.
Um, It's good that they gave us a tricky enough example as
Yeah.
as a small example. Yeah. I think we should stop now, and
Yeah.
tomorrow we can meet and we can do the flooding thing,
Okay.
which may be easier, and then we will have only this and tomorrow's puzzle and the other one that is still missing. So it will still be 3 days behind.
Yeah. Okay. All right.
Yeah.
Well, that was an intense session. So,
Indeed.
And congrats to both of us. But yeah, especially
Yeah, turn
you
on
with
your
some of
camera so
those.
we can say goodbye.
All right. Can you see me now?
Yes.
Yeah. Cool. Yeah. So, yeah, that was intense. I am definitely fried. I don't think I'm capable of thinking anymore. So I'm gonna go take some lunch. But yeah, that was fun.
Yes, that was fun.
Have you seen these memes with these like these people after like cage fights with like battered faces and like totally bruised, and they're like, "Yeah, I had a lot of fun. It was really good. I learned a lot." Feel a little bit like
Yes.
that.
But I think we are making progress. We have solved 1.5 days.
We have. And how's your availability next week generally? Are you more available or less available?
I am more available, so I can do mornings if you prefer.
Great. So I think we might be able to catch up with it next week.
Yeah.
But the problems are definitely getting harder.
Yes. And do you want to do 10 a.m.?
Yeah, that'd be great.
Okay, so I see you tomorrow, Monday, 10 a.m. UTC. Thanks for this, and thanks to everyone here on the chat, Not Was One, and Tail, and Bo. I see you all again tomorrow. Enjoy.
Bye-bye.
Take care.
Bye.
Thank you for watching the stream, you know how great it has been. Or maybe it sucked, and I am glad that you stuck with me. And soon we'll all be back together for some more coding or talking or chilling. The next time I'll be streaming.